Good morning, everyone. I hope I'm clearly audible to all of you. Welcome to the workshop on generative AI. So we actually had quite a bit of overwhelming responses for this. We had like 500 people signing up. Let's see out of the people who registered, how many will come. It's a Sunday morning, so joining at 9 can be challenging as well. It's challenging for us also. This will go on for the about 5 to 6 hours with a break in the middle as well. So we plan on covering quite a bit of interesting content. When we were planning the content, it turned out to be quite well. So we'll see what they are. Just to give you an idea about today, we'll start with a brief introduction about the motivation of doing these workshops and some of the other work we have done so far. Then we'll go to an introduction to the department and some insights, mainly about AI. And we have the keynote from Dr. Sadeep Jayasumana. He will be talking to you about AI and an intuitive understanding of it, mainly. So we'll get to that. Then we'll go to our content, mainly on the learning aspect of it, what we plan to cover by the time we finish the workshop today. So that's a very brief about what you can expect within the next few hours. We'll have a break as well in the middle so that you can get refreshed and come back. But we hope by the end of today's session, you will have a pretty comprehensive understanding of generative AI, where to start. Of course, we are unable to teach everything from A to Z within one day about generative AI, but we'll cover the overview and give you the necessary material for you to take things forward from there. So that's what you can expect to see for the rest of the day today. Having said that, let's move into the first presentation that we wanted to cover. That is mainly introduction to SkillServe, what we have done so far and what we plan to do in the future as well. So I hope you can see my slides without any issues. I will only take maximum 10 minutes and then go through this, and then we'll hand it over to the next speaker. So speaking of a brief history of SkillServe, wanted to tell you how this started and our motivation, where we are right now, what we have done so far, and what you can see, what you can expect to see in the future. So in 2021, these two gentlemen, Kitmin and Abba, they were working on something called the missing semester. This, in fact, began even before 2021. You might already be familiar with the concept of a missing semester, but if you are not, the idea is you have a certain set of modules that you cover when you go through the university. When you do that, there are pieces of knowledge that are not covered through these modules. That might be because the curriculum is not refreshed. Maybe when the curriculum was designed, few modules, they were not possible to include them. For whatever reason, things that should be there is not there. So that is what we refer to as the missing semester. So they were working on this because they have graduated by then, and they looked back and said that, okay, it would be better if we learn these things. So with that intention, few content or course materials were put together. This was mainly done within the Department of Electronics and Telecom Engineering at the University of Moratuwa. And after compiling them, we got in touch. I also got in touch with them. And then we started thinking about, okay, these things are missing in the university curriculum. Why don't we make things available to the public as well? Other universities or anybody else who is interested in learning. Then the problem is you cannot go with, like a advanced course initially to the public. So we brainstormed, okay, what is lacking right now if you have to teach something to the public? What is the requirement? So many people were teaching things like software development, web development, machine learning. So we thought, okay, we are the electronics and telecom department. So why not do something in electronics? So around March of that year, we started formulating this course that is an embedded systems workshop for beginners. So with that thought, we developed this content and we did a series of four workshops, as you can see. So this was a huge success. Many people turned out. And surprisingly, typically what happens is for the first workshop, many people come. And by the time we reach the last workshop, about 10% of the people who came to the first workshop come to the last workshop. In fact, many people who came to the first one ended up coming to the last one as well. So the retention, if I'm to use that term, the retention was really good. Then it gave us the impression that there is in fact a requirement for electronic education among the general public. Then the problem was, if we are to cover a larger content or a bit of more content that goes beyond 4 weeks, then it becomes, a bit more challenging because it's like a one semester's module, right? If you have to expand this 4 weeks content to, let's say, 12 or 16 weeks, that is like one semester in a university. So the first workshop was a free one, but to expand it to 12 or 16 weeks, it was difficult to make it in the free mode. So therefore, we came across this opportunity from the American Center in Colombo. They had a grant promoting education. So we applied for that, and fortunately, we got it. We got the grant. We were successful in our application. So with that, we expanded our 4 week curriculum into 12 weeks. So now this covered more material. Even for this one, a lot of people turned up because again, it was free of charge. Then I think if my memory is correct, more than 100 people completed and we got really good feedback. And then we thought, okay, how can we sustain this? Of course, the American Center in Colombo is not going to fund us every time. So therefore, we'll have to charge something from the participants if you have to make this happening like frequently. If you have to recurring, in a recurring mode, if you have to make these courses available, then we have to come up with that model. So with that, we developed a very comprehensive curriculum around it. We looked at what went wrong in our free workshops. We got learning outcomes from that. We changed some of our work. And then we came across this philosophy, which is to develop relevant and high quality content. We don't want to do another Me Too product, something that is already out there. We don't want to copy and do it by ourselves. All the courses should have hands-on experience. It should be outcome oriented. So these are our core values when we were developing courses. So the reason for thinking that way is that we noticed that most courses, especially in the university system, we teach people so that they can do research. They are very theory heavy. But we wanted the SkillServe courses to be more practical or outcome oriented. So the structure that we have adopted in all our courses is that we have a project. That project is our outcome. And we teach the theoretical aspects so that somebody can achieve that outcome, that objective, or that project. So by the time you finish the course, you have actually built something. In the case of the microcontroller course, the first one, the basic one, in this case, initially we had two projects. One was an electronic device that reminds people to take medicine on time. The second one was a smart plug. So during the course, we realized that doing two projects within one course is challenging to people. People were finding it difficult to understand. So then we removed one project and then we settled on one and we went very deep into that one project. And we enhanced it as well with a bit of an IoT component. So that was the structure. And every course we have developed subsequently followed this same philosophy of defining the course first and working our way backwards to develop the course content so that you can learn the material to develop that project. So with this, we have focused on three main areas: IoT, computer architecture mainly, and we did one course in cybersecurity. Under the topic of IoT, we have so far conducted the microcontroller-based embedded system design course. This is the very basic course where we start from blinking an LED into developing a product in IoT. Then the second course is embedded product design for IoT. This is a more advanced version of it. So here in the first one, we don't talk about things like AC to DC, power electronics. There's nothing like that. PCB design work is basic. Firmware is again basic. But in the second course, we take a more advanced approach. Here we design a smart plug so that one that got separated went into this with a lot more detail under the embedded product design for IoT course. The third one is embedded machine learning for edge computing, which is happening right now. So I'll get to that. So this is the microcontroller-based embedded system design course that I've been talking about. So far, we have had 3 intakes: July in 2021, November 22, and January 24. So by looking at these dates, I think you can realize that approximately every one to 1.5 years, we have an intake and we teach people on the basics of microcontroller-based embedded system design. This is the second one. We have had one intake so far. And the third one, embedded machine learning for edge computing. We did one intake in September, and the second intake is happening right now. So in fact, I will show you the website at the end of this presentation. If you go to that website, you will see that the registrations are open for this course right now, with the deadline in a few days. We did one session introducing to you what the course is. That video is available on the web page, so you can refer to it, understand what this course is going to cover, and if you are interested, you can sign up. Moving on to the second interest or the focus area, that is computer architecture, we have conducted one course so far. That is the System Verilog one, the basic one. We are planning for the second one as well. But before that, since it's been some time, it was February 2023 when we offered the first System Verilog course. We are planning to offer another iteration of this towards the end of this year. So Q4 of 2024, you will see another iteration of this course coming up. And in terms of cybersecurity, we recently concluded one. The September intake happened. So this concluded around January of this year. Here is a group photo of one of the courses that we conducted. Typically, for the courses that we have done, for each intake, about 40 to 60 people would sign up. For the System Verilog one, we got 200 plus, but typically the number stays around 50. In addition to these courses, we have also done free workshops. So here is one, Introduction to Quantum Computing, and the other one, Introduction to Generative AI. Now that you know what we have done so far and a little bit of what we plan to do in the future as well, I wanted to touch on one key initiative that we are working on for 2025. So something that we have understood, especially with the amount of interest that we generated for the System Verilog course, the amount of learning material, especially for the area of FPGA, ASIC, chip design, or in general, that is lacking. And when you talk to the industry in Sri Lanka, they say that there's not enough engineers for them to hire. They actually want to hire a lot of people, but they can't because they don't have the skills. The engineers don't have the skills required to work in this area. So right now we are working on a comprehensive set of modules starting from the System Verilog course so that we can popularize this area in Sri Lanka. We plan to work with mainly the Sri Lankan diaspora living outside of the country. They can be academics, like professors. They can be working in the industry. We work with them to develop a very solid core content for this series of modules. So this you can see coming up in 2025. And the good news here is that, like I said, any course that we develop, we want it to have an outcome. So if you're teaching chip design, designing an actual chip and manufacturing, that should be the outcome, right? Otherwise, there's no point. So therefore, I'm not sure whether you know, but what we call the taping out or the actual manufacturing process of a chip, that's a very expensive exercise. You cannot go and get one chip out of a fab, right? Even the very popular these days, NVIDIA, even NVIDIA does not have fabs of its own. They work with TSMC. So it's a very expensive exercise. And I hope the reasons are clear because of the manufacturing process. It should be very controlled environments. You can Google, you can look at videos on YouTube. Then we started thinking, okay, if we are to actually get a chip out of this, what do we need to do? So we reached out to several partners, and we are happy to say that at the end of this course, without having to pay an absurd amount of money, we are getting sponsors from the industry as well. Those who sign up for the courses, this will happen. We'll give you more details in the future. Those who sign up for the courses will actually be able to get a chip at the end of the course. It's not one course, it's going to be a series of courses because there's no way where we can teach the basics and go all the way up to the point of manufacturing a chip in one course. That's in one semester. That cannot happen. So we have a series of courses, but anybody interested in this area can take those series of courses and have a chip fabricated at the end of it. Right? And by the way, that doesn't mean that you come up with a bad design and then you can get it fabricated. Those who complete the course with all the exercises, assignments, you will be able to. Right. So that's what you can expect to see in 2024, a bit more focus on the ASIC or SOC side of things. Along the way, we have had several parties supporting us. Synopsys is one of the giants in the EDA, electronic design automation industry, and they have acquired a company in Sri Lanka like 10 years ago, I think, and they have a presence. So that's a huge strength for us, especially when we are designing the curriculum for the ASIC roadmap as well. Then we've had UBC coming in, IEEE Young Professionals Sri Lanka, and of course ENTC, where it all started, and Uni Consultancy Services of University of Moratu as well. So I think that gave you an idea about what we have done so far and what we plan to do in the future. We want SkillServe to be a place which empowers Sri Lankans to be industry and life ready. We are right now working on the industry part, not the life part. That will probably happen in the future. But that's our vision, and that's where we want to go. If you go to skillsurf.lk, you will see that the embedded machine learning for edge computing course is currently available for registering. So you can sign up, those who are interested. And to wrap up, I wish you all the very best and happy learning in the generative AI workshop. Thank you.
Thank you, Dr. Subodha, for introducing SkillSurf. I'd also like to welcome Dr. Ranga Rodrigo to give a small welcome to the audience and also background about the Department of Electronic and Telecommunication Engineering. Thank you.
Thank you, Kitmin. Thank you for the opportunity given for me to say a few words. So Dr. Sadeep Jasumani is joining, and Dr. Subodha Charles himself. And then Kitmin, you are joining from British Columbia, and Apam is joining from Germany, I think, and all the seniors are joining. Thank you very much for joining and helping. As Dr. Subodha Charles mentioned, what we want to do is to make the knowledge that the department has available to the public. As you know, we cannot recruit more than 115 students due to the facilities that we have at the department, but there is a lot of knowledge in the department right now. In electronics, in FPGAs, in telecom, in computer vision, and in AI, the knowledge is very huge. So therefore, we want to make that knowledge available to the public also through these seminars. This is why we want to do this. So after I came back to the department in 2008, I have been working on computer vision problems. So naturally, we embraced generative AI also. So Dr. Sadeep teaches a class. I think he will start teaching the class in very soon to the final years. So with all this, the knowledge has been gathered. So as Dr. Subodha mentioned, in this little seminar, Dr. Subodha will deliver a program where you can actually get things done. So two very exciting projects will be done in this few hours today. So keep your eyes open and truly participate in this. I think the benefits will be very big because those who have the true understanding of generative AI will be training you in this program. So I wish you all the very best. Thank you very much. Present deliberations.
Thank you very much, sir, for that talk, and yeah, very appreciate you being here as well. I think I can give the stage now to Sadeep. Just a small introduction about him. He's a research scientist in AI at Google in New York. So very excited to have him.
He's a staff scientist and he's a very big person now.
Yes. I'll post the recording, Dr. Sadeep, so that you can start giving introductory speakers have been covered. So I'll invite Afam to start the first session. And Afam, you can also introduce yourself. Yeah, the stage is yours. Thank you.
Hi, everyone. I hope you all can hear me. And
yes,
let me share the screen. Can you also see my screen?
Yeah, we can see it, Afam.
Okay, thank you. Right. Really good to have you all. So this session will be a starting point of the contents of this workshop. And I will be talking about the basics of attention mechanism and the transformer network, which is essentially the fundamental block of the generative AI, which you have had the high level understanding from Dr. Sadeep's talk right now. So a small introduction about myself. I'm a graduate student right now at Technical University of Darmstadt in Germany. I used to be an AI resident at Meta AI in New York last year. And I was also a research intern at MBZU AI in United Arab Emirates. I did my undergrad degree in University of Maratua in the ENTC department itself. I also want to highlight some acknowledgements of the contents I have borrowed from the open source courses available online, and I thankful to the authors of the courses and the blog post. All right, let's get started. The high level, the agenda of this session is going to be, I will be initially going through the timeline on how everything started. And then we will dive deep into what attention is and how the transformer block is like how the transformers are built up and how exactly it's been used in these days in a like not so deep or not so high level understanding. So we'll go through the fundamental building blocks of everything. And then later on, we will be building a small version of a GPT, which is a natural language processing model where you can generate text similar to ChatGPT, but a very minimal version of it. And then after that, we'll come back to the models and we'll talk about some of the interesting applications or other interesting new networks that came up in the recent days in terms of natural language processing arena. So talking about the history of natural language processing and the generative AI, before long, like around 2000s and 1990s, we used to have recurrent neural networks and LSTMs, which used to do the sequential processing. Sequential processing in the sense we have multiple inputs and multiple outputs. One example is machine translation task. You have one language, let's say in Sinhala or Tamil or German or French, and you have to translate that to English. It will have multiple input, which is like, which could be essentially words, and then it could be translated to English. So that particular task is used is done using methods called RNNs and LSTMs up until 2017, where a big boom happened in natural language processing, the arrival of transformers, which is essentially a neural network that does this sequential modeling in a more parallelized way. We'll come back to that later. And then once the transformer has arrived, there has been a lot of progress in the natural language processing domain with the arrival of new versions of new variants of transformer models and like multiple scalable transformer models. And also the generative AI era has begun in the early 2020s with the advent of like much complex compute powers and a lot of like a lot of huge models, which we call large language models, which we will also talk about at the latter part of this talk. So a brief history on how it all began. So people used to encode words in terms of like embeddings. So basically, we have to encode like computers cannot understand computers actually cannot understand the what do you call the words. Basically, you have to give numbers to the computers. So basically, we need to provide more discrete representations, and word embeddings have been found to represent each word in terms of vectors. But the problem there is like there is no context. For example, like if you have some word, let's say mother, there is no content for that, there is no context for that. It's been encoded based on like how it is represent across all the web pages in the internet. For example, maybe like Wikipedia pages, and like we would know like words might have different meanings across different sentences. So there has to be some sort of context has to be encoded in the word, because like in different sentences each word could mean like different, and we will come back to that, what does that mean. So basically, this is sort of a starting point how words are sort of like started to be embedded as vectors in the past, and some examples include word to vector, glove, and bird, which is also a transform model, and also Elmo. So and then like we have a sequence to sequence model, which I touched upon earlier. So some examples are recurrent neural networks and LSTMs. We will not go to the detail of the sequence to sequence models, because this is pretty much not being used a lot in these days, because after transformers have arrived, people are being used a lot of transformer networks rather than sequence to sequence model. But like just to give a touch upon on how it all began, like the LSTM networks are being used before the transformers to do this sequence to sequence task, where you will have multiple inputs and multiple outputs. So there used to be a dependency, like which sort of identifies the context of the sequence, and you also have like information flow across the sequence to understand the context and learn the information flow based on them. And then like as we noticed, like there are a lot of challenges in sequence to sequence models. The very basic challenge is it is unable to handle very long range dependencies, because like it does not have like a concrete contextual understanding for long sequences. If you have a very long sequence, like the model is unable to capture the context for that particular sequence. For like, let's say like we have like a big description of sentence, and like we'll have to understand what is mentioned, like, or maybe like we have to translate that to another language. So translating a huge sequence is not possible, or rather it's computationally expensive when it's come to sequence models. And also like since it is like you can see this from this architecture, like xi is like the input, and um, output is there. So it does this input output thing one by one, like as in like sequentially. That means it is unable to do things parallelly, which will also yield too slower processing time. And we will have this like usual problem in deep learning that's called vanishing gradient. If we have like very long sequences, there is an issue of vanishing gradient, where like during the gradient backpropagation, the gradient goes near to zero, which makes the model not to learn a lot from the context of deep learning. So talking about, these are like sort of the challenges of sequence to sequence models. And then came a new model in deep learning called transformers. This paper named Attention is All You Need has introduced this transformer network. Initially, it was introduced for machine translation task. And we will be, for the rest of this talk and like for the rest of this workshop, where we'll be mostly focusing, or we'll be like solely focusing on the transformer networks, because this has changed the way the world has seen the deep learning. So this will be sort of the recipe for our workshop today. And we'll talk about the building blocks of this transformer network. And this has been introduced by Google. And still you can see, according to Google Scholar, there are like around 120,000 citations, and it's still exponentially increasing. So this has been a big like an advent in the world of deep learning, and there has been a lot of applications still seen using transformers. So some key facts about transformers, like as I said previously, it has been introduced initially for machine translation task. For example, the input which is in French can be translated to a students. You can see this is also a sequence to sequence model, as in like if you give an initial sequence as an input, it will produce a sequence as an output. But the only advantage over sequence to sequence models we had previously is like it could do things parallelly, which is like they introduce a new mechanism called self-attention, which we will go through in detail in a couple of minutes. And the self-attention enables the model to do the parallel processing across the entire sequence, and it actually speeds up the training and inference, and also like comes along, like also overcomes the drawbacks which we have seen in sequence to sequence model. For example, the vanishing gradient problem or other long range dependencies. Everything is sort of like been overcome by the choice of architecture which transformer has proposed, like thanks to the self-attention mechanism as well. So these are sort of the key facts about transformers, but like we should know like attention mechanism is not exactly a new thing that transformers came up. Like there has been attention, the talks of attention prior to transformers as well. So let me talk about what is actually attention in the context of machine learning. So basically, considering this sentence, the animal didn't cross the street because it was too tired. If you consider the word it, for us humans, it is like very easy to understand. It refers to the animal. We don't know what animal that is, but like we know for sure that the term it refers to the animal. So basically, as humans, we have this textual intelligence based on what we have learned previously and based on all the experience we had, like we know what that corresponds to. But it's not easy for a machine learning algorithm or a deep learning algorithm to understand directly what does this contextualize. So that aspect is basically called attention. We need to basically, like, given a particular word, or rather we call it token in the context of deep learning, given a particular token, how much of an attention it has across the given sequence, or rather given the context is so how much of focus you have to keep on that particular token is the attention. For example, an illustration can be seen in the right picture, where an attention mechanism shows the it has to be focusing a lot on the animal part, where like it's highlighted, which means it is sort of focusing more on, like, attending more on the animal, which means we have to give more attention to the animal. So this is basically output captured from the output of a transformer block, which means it has learned the context very well, and the term it refers to the animal in this context. And we also talked about attention being there prior to transformers. There has been talks of attention prior to transformers, as I said, like in this paper, in neural machine translation before transformers. They talked about the importance of attention while doing the translation, while doing machine translation. For example, in this particular network, I'm not going to go deep into the network structure itself, but I just want to give you an overview of the importance of attention. So this alpha T1, T2 gives you the attention of this particular token given the whole context. And you can see in this heat maps, while translating from French to English, the focus is, like, you can see the attention map. For example, the term in French corresponding to European English in English has much more attention between each other, which means like whenever translating this word, like, and let's say you are sort of like getting a dot product between these two word vectors, you get more sort of highlighted value, which means like the attention is very high. So there have been attention in sequence to sequence model, but like the problems in sequence to sequence model still persists in the context of deep learning previously. So they have to come back to a new model called transformers. And you could also like notice some of the prior attention works in image captioning as well. For example, like when you notice like when you have to caption words or rather caption an image, you could notice here, for example, a woman is throwing a frisbee in the park, and like whenever this word is sort of generated or rather captioned, you could see which part of the image the model is sort of focusing. So it focuses on the frisbee, and like if there is a dog standing on the hard floor, it focuses on dog, and like similar to and like similarly other images also attend to like whenever generating that particular word or rather that particular token, the model is trying to focus on that specific part of the image to make sure that the word is correctly generated. So these are some of the prior works in attention, I would say, before transformers. But like transformers actually boomed up the way the attention has been seen, and the major building block of transformers is self-attention. So this is the transformer network, and this transformer network comprises of two major components, which is transformer encoder, and transformer decoder. Transformer encoder is the part on the left, and the transcoder decoder is the part on the right. And you could see there's multi-head attention, feed forward, and add and normalization. So positional encoding. These are like key concepts of transformers, which we will try to go in depth during the course of this talk. And the major fundamental aspect that they have introduced is self-attention. Self-attention is basically having an understanding of the input sequence itself. Let's say you have an input sequence which you have to translate. How much of an attention, let's say you have a French sentence, and like you have a particular word, and how much of that word is important in the context of the whole sentence is basically self-attention. And they have also introduced this in particular formula for attention. QKV corresponds to query, key, and value, which we will go into the detail later. And for those who doesn't know what softmax is basically like given a set of numbers, or maybe vector of numbers, it converts that set of numbers to probability distribution. So probability distribution, and then the summation of that probability distribution corresponds to 1. So that is basically the softmax function. And when we will now like discuss deep into the self-attention mechanism, which has been introduced using like in this transformer block. And we'll also talk about some of the other aspects, how this transformer is built up. Like we'll initially talk about the building blocks, and then we'll combine them together to see how exactly this transformer works in the context of a machine translation task. But like we should know that it has not been limited to machine translation. It has been used in variety of tasks across natural language processing and also like computer vision these days. So but for the sake of this talk, we'll stick to image translation, where the machine translation, where you have given a sentence in one language and you have to translate it to another language. So let's see, for example, the phrase the brown dog ran. So basically, in talking in numerical terms, we'll have like xi's, which are, we call them tokens, but essentially like it has not to be individual words. Tokens have a different meaning in deep learning, but like for the sake of simplicity, we will discuss each token as each words. So x1 is the, x2 is brown, x3 is dog, and x4 is ran. So basically the goal of self-attention, the transformer paper has introduced, is to create sort of a contextual representation, as I said previously, zi, which in this case z1, z2, z3, and z4 of the input sequence. For example, how much of the context does z1 has given the whole sequence, and similarly, how much of a context does z2 have given the whole context, the sequence. So that is basically the goal of self-attention, and we'll see how exactly it's been done in a while. So basically, as I said previously, like Z1 will be sort of, there'll be a weighted contribution of all the tokens, in this case words, and how much of a weight it carries. Like, let's say, for example, Z1 is the contextual representation of the token X1, and how much of a focus does the other tokens have to give to that particular token to provide this, to create this contextualized representation. That's basically the idea. That's basically the high level understanding of this contextual representation, which is basically which we basically do using self-attention. Yeah, like as I said previously, like this attention mechanism, like A11 is basically how much of a focus you have to give to this particular contextual representation of X1. To proceed with that, calculating, or rather finding the self-attention representation, we'll have to come back to the attention equation, which I have shown previously, which is this particular equation. As I said previously, we have three elements here: query, key, and value. So similarly, we'll have to okay. So each token, as in each word in this case, has three associated vectors for them. So query, which is qi, and key, which is ki, and value, which is vi. We'll have an understanding of what it exactly represents while we go through the self-attention process. But like for now, we'll need to understand that xi will have like every token in a sequence will have three associated vectors: qi, ki, and vi, query, key, and value. And how exactly those are generated? So basically, each sequence, or rather like a whole sequence, will have weight matrices. In deep learning, weight matrices are sort of, we call parameters, where we will train those, make those parameters learnable. So these weight matrices are the ones making the deep learning networks, deep neural networks, learn. So that means, like, let's say weight matrices are like, you have a matrix, and there are like some numbers in the matrix. So over the course of training with like multiple sources of data, those numbers tend to change, like those are like changeable. And then, like, according to the data and the way you train, those adapt towards a more representative numbers. That means, like, if you give an input, and like it should give an output, and that's like more meaningful. Initially it will not be the case, but like over the course of training with different data and like learning methods, you will get to a situation where the weight matrices have meaningful representations. So basically, for each vector, query, key, and value, you will have three weight matrices, that is wq, wk, and wv. And these associated vectors, which is qi, ki, and vi, they are obtained by multiplying the weight matrices with the sequence tokens. So for example, you have x1, you have a vector which is corresponding to the x1. Like, as I said, like it will be embedded in numbers, not the word itself. Initially, it will be embedded to a number. And then you'll have q1, k1, and v1. which essentially will be x1 times wq is q1, x1 times wk is k1, and x1 times v is v1. So that's basically how the associated vectors are generated. That's like the first step of self-attention. And then we will have now we'll start the process of self-attention. Essentially, we'll step by step go through the equation that I have shown previously, the attention equation. So how exactly is the self-attention calculated? So we'll go step by step. For each token, we'll initially calculate the scores. Like we'll say scores S1, S2, S3, and S4, which sort of represent how much attention you have to pay in between each other. It's essentially a dot product between query and queue, query and key. So for example, if it is S1, if you are calculating S1, you are just doing a dot product of Q1 and K1. And if you are having a dot product of S2, you are multiplying Q1 and K2. Similarly, for S3, it's Q1 times K3, and for S4 is Q1 times K4. You have to note that this is not done individually, as it will all be processed using a giant matrix. This will all be done parallelly using matrix multiplication. So in one matrix multiplication, you'll have access to all these numbers, all these scores and everything. And even the whole attention will be calculated using like 1 or 2 matrix multiplication. So I'm just breaking down the steps here to give you an understanding on how exactly this works. So once you calculated the scores, you will then have to like normalize, as in like we'll have to divide it by the square root of the length of the key. So this we call, in the context of deep learning, we call it dimensionality. So we'll have to divide it by the square root of dimensionality. The reason for this is basically normalizing. So we'll have to normalize the attention vectors we have generated to make sure that we don't explode in terms of numbers. So that is basically happened here. For example, if you see the initial score values, which are like in tens, sometimes in hundreds, and you normalize it to bring it down, and you also softmax it. So you do this softmax. If you recall what is softmax, like it basically takes a set of numbers and then applies a probabilistic distribution on top of it, which means it will boils down to a 0 to 1 representation, and the total of that will be 1. So if you add these all up, it's going to be 1. So basically you get the scores and then you divide it by the dimensionality of the key and then do the softmax, which will essentially give you some self-attention values. So once everything is done, so as I said previously, so that is basically the initial component of self-attention, and we'll have to multiply those scores with a weighted multiplication of the values. So we have used query and key yet, and now we have to use those scores we have multiplied, use A1, A2, A3, and A4, and we have to multiply them using the values we have obtained by multiplying the token value using the weight matrix for value. So that's like 0.87 times V1 plus 0.12 times V2 and 0.01 times V3. So this will basically yield us the contextualized representation for the token 1, right? So similar to this, so this is basically the contextual representation of token 1. Similar to this, we'll have to do for each token. For each token, as in like we'll have to do another sort of representation for Z2. In this case, we'll have to recall the query key multiplication. For example, this A1 is not similar to the A1 we have mentioned previously. So at this context, like to calculate Z2, we'll have to take query Q2 times K1, K2, K3. So basically, it has to, the query and key values has to vary depending on which contextual representation you are trying to build up. So basically, this is sort of an idea on how you build the contextual representation. So similar to Z1, Z2, like you'll have to get all the contextual representation for all the tokens. And this is basically it. So basically, self-attention, as I said, it tries to bring you a contextual representation by looking at all the sequences and give you like a more compact and contextual representation of the whole sequence. So once the self-attention is done, now we'll see how exactly it is applied in the context of transformers. But like before that, we should know that self-attention is very powerful. It's not just the matrix multiplication and the mathematics we do. If we do this for like numerous times and in the context of like big matrices or big sequences, people have been showing like it actually studies the underlying context, underlying what exactly the sequence is trying to tell, what exactly is the underlying understanding of the sequence. Or let's say if you're trying to translate a passage in French to English, it tries to understand what exactly is in the whole passage. So self-attention is actually powerful. But still, to the most cases, it's still basically a black box, and in most of the cases we don't know actually what it's learning, but we are trying to see what but we know for sure it is learning something, but like there has been complication on what it is exactly learning. So a takeaway message: self-attention is powerful and allows us to create great context-aware representations. All right. So how exactly is the self-attention contributing to the building up of transformer encoders? So transformer encoder, as I said previously, transformers have like two different main components, which is transformer encoder and transformer decoder. So transformer encoder itself consists of multi-head attention, feed-forward layers, layer norm, residual connection, and positional encoding. But like there is no self-attention here. But the thing is, self-attention is not being used one by one. Like you could say like self-attention is an easy math calculation. You just do some normalization and dot matrix multiplication. But the thing is like there is a huge parallelization going on in self-attention, and it creates this multi-head attention, and we'll see like how exactly it is being formed. And there are other components that is essential in the building block of transformers as well, which we will see in a moment. So the first one is feed-forward layers. Feed-forward layers are essentially like MLPs, which is multi-layer perceptrons, or we call it standard neural networks. So I just want to recap on like where are we right now. So we want to translate this phrase, the brown dog ran. And at this point, we have calculated the contextual representation using self-attention, and we have this self-attention head. This is we call self-attention head. So we have the results from the contextual representation. So basically, now we have like four representing this particular sequence. We'll just input this to a feed forward or rather multi-layer perceptron and get some output R1, R2, R3, R4. Now, please understand that when we are like learning, or rather when we are processing this self-attention head, there is a communication between these tokens. Like for example, if we calculated this Z1, like we are multiplying this query Q1 with other key values, and like we are like multiplying this particular scores we have calculated with all the values. So basically there is a communication happening in this self-attention head, but there is no communication as such in feed-forward neural network. It just takes this Z1, Z2, Z3 as input, and there is going to be a neural network, a standard linear neural network, and obviously there is going to be an activation function. The activation function is GELU, and it will output some vectors, namely R1, R2, R3, and R4. So that's basically feedback layers. And then we have the residual connection. So basically what residual connection is, if you see this particular transformer encoder layer, so this, like the skip connection, is called residual connection. So basically the input embedding here, like some embedding vectors here, are being transferred without sending through the multi-head attention directly to the maybe the other step, or from like some after processing through multi-head attention without sending to the feed forward network, we can also do skip connection, skipping the feed forward layers, transforming directly to the other step of the processing. So basically why exactly this is happening is, if you recall, sequence to sequence models used to have this vanishing gradient problem. And as I explained, vanishing gradient happens if there is a long sequence, and during the gradient descent, which is the traditional way of learning deep neural networks, the gradient used to reduce. I don't want to go through the mathematical details of it, but like the gradient tends to reduce, and the information flow across numerous layers does not happen. So to avoid that, if we, rather than processing through a neural network, if we can directly have a connection, a skip connection, directly have a skip connection to the other layer, the information is like basically the ensurety, the guarantee of information passing through layers is very much happening. And basically it helps understanding the long context, or maybe it actually have a long range dependency as opposed to sequence models, which we have seen previously. So basically, like once we have, like the residual connections are like twofold. One is happening before the self-attention head, like one is there after self-attention head. So there is a residual connection which does this, which mitigates this problem of vanishing gradients. And also we have layer norm, normalizing across multiple layers. This is just for the stability, like a standard normalization to ensure the stability and proper gradient flow. So basically this is like a standard component in the transformer network, and people have been discussing or maybe investigating on different sorts of normalization. But like normalization seems to be essential because it stabilizes the network in terms of the, rather than exploding the vector numbers into tens and thousands or even millions. So as I said previously, you could see like one of the problems in sequence to sequence modeling is it processes each word sequentially, and I said the transformer model mitigates that problem and it processes everything parallelly. But there is a problem in that, like we have x1, x2, x3, and x4. We know that this is in order, but like the model doesn't know. The model doesn't know this is the first token, this is the second token, this is the third token, because it's processing all in parallel. So we'll have to put some sort of encoding there, like mention to the model, okay, this is coming first, this is the first token, this is the second token. And that's done using this interesting terminology called positional encoding. So this is essentially mitigating the issue of the mentioning the process, the positions to the model. And there have been several positional encoding methods. And the original transformer paper used a sign cost positional encoding method, and they have reported results on what works best in different context for the particular machine translation task. So basically, it encodes some position along with the token. Let's say you have a vector representation of the token. And then like before that vector representation, you mention, okay, this is coming at this position. So basically, that's the positional encoding, and that's also a crucial component of the transformer encoder layer. And now we'll come to multi-head attention, which is essentially a sort of stacked version of self-attention, which we have seen. So let's see this attention head as one attention, where you do like you have a weight matrix W0 for query key and value, and you do the same processing as we have discussed for the self-attention layers. And similar to that, you have several attention heads. So attention head 1, it can go up to 1632 and all. So every attention head has different sorts of weight matrices initialized. So basically, it will generate different query key and value pairs, and it will essentially generate different values while learning. So the reason for that is basically, if you have like multiple attention heads processing in parallel, it tries to understand the maybe like you could say it tries to understand a same passage. Maybe you want something to translate, and it understands the same passage but in different perspectives. One attention head focuses on one particular aspect, and the other attention focuses on different perspective. So basically, combining the knowledge from multiple perspectives give you a holistic understanding of the sequence you are trying to process. So basically, that's the whole idea of why exactly this multiple self-attention heads are using. And these multiple self-attention heads are stacked together, or the multiple self-attention heads are stacked together to form a multi-head attention. Let's say, for example, here you have 8 self-attention heads, and it is all concatenated, and it's all concatenated to form concatenated like a contextual representation. And you will essentially have like an ensemble or maybe combined perspective of all attention head on the context of the sequence you are trying to translate or maybe process. So that is basically how exactly the transformer encoder is built up. If we go back to the transformer encoder, like you will initially have the inputs, which I showed you, like some sequence or something. The input embedding is essentially transforming each token to a word to vector. And then like we do positional encoding to make sure which position each token is corresponding to. And then we will have a transformer encoder layer, which will comprise of multi-head attention, which is a stacked version of self-attention heads. And then you will have a skip connection, which is a residual connection, which is mentioned here as add, and layer normalization. Then we'll have feed forward and so forth. So this is basically a fundamental transformer encoder layer. So the transformer encoder layer will essentially give you a representation of what is inside the sequence you are trying to process. Generally, a transformer network will not consist of one particular encoder. It will have multiple encoders stacked upon each other, and it will yield a complex but rather a meaningful representation of the input. So basically, we will going to have multiple encoders stacked upon each other, but if every encoder will do the same process that we have discussed previously so far, the self-attention, the feed forward, everything is going to remain the same. So once it's processed to the encoder, now we'll have to now once we have processed through the encoder, we have this representation R1 to R4, which essentially encodes this particular input sequence, like basically a representation of the input sequence, like a numerical representation. But now the numerical representation itself is not useful right now, because our task is to translate that to a particular another language, which means like we'll have to, like once it is encoded, we'll have to do the decoding part. Like it's like once encoded, we'll have to do the decoding. That's why we have transformer decoder. This is basically has the similar contents, or rather similar building blocks to the transformer encoder. You will have output embedding, which is essentially the word to vector, which transforms words to numerical representation, and then you will have positional encoding. Now you will have masked multi-attention heads, which means I will come back to that in a moment, what this masked part is. But like one thing to note here is for this particular multi-attention, so this you can think this as self-attention, because it does the attention for the output tokens. And this multi-attention takes input from the encoder. So the encoded representations acts as key and value to this particular multi-head attention, and then the output from the self-attention head acts as the query to the multi-head attention. So in a more illustrative way, let's say you will have encoders, 8 encoders. It will produce more contextualized embeddings of each token. And then once each token is encoded, you will have decoders, which will, like every decoder layer will get input from the final layer of the encoder. And then it will process the whole sequence as it is in the encoder, and then it will generate the translated sequence. Just to give you an idea here, for example, so this translation, you could see this the video playing. So basically every time step it will process this particular sentence parallelly. It does not happen like one by one. So it will process the whole sequence parallelly, like using multiple encoder layers, and then it will be encoded into different sorts of contextual representation. And then you will have decoders, like each decoder layer will have access to the encoded representation and use them during the attention process. Once like this is how exactly the output is created for the translation. For each time step, it is trying to generate only one word. Like basically, like it processes the whole sequence at once as an encoder. But like when decoding, it does so initially you will have an output of like I. So this is basically translate to I am a student in French. And once you have like a initial, like a start of the sentence, or maybe like initial token named I, the transformer decoder will try to predict the am as the next token based on the encoded representation. And once you have I am, it will try to produce a and student. So every decoded sequence is produced one by one. So that is basically the like the masked multi-head attention. So in a more precise way, like let's say you have like this has to be translated to I am a student, which we know for sure. And we don't feed that whole output to the decoder layer, because that will have access to the whole translated sequence, and it will know what it has to generate. But rather we will initially, to generate the first term, we'll only give the term I and say, okay, what could be the next term? It will generate I am. And in the next time step, we'll give I am, and it will try to produce so at each time step, like it will produce one sentences one by one. So this is basically like a general like a very standard or maybe very basic machine translation task. using transformers. So now we have done encoders and decoders. Also, please put forward any questions if you have in the I think the link they have shared, so that we'll come back to that the questions, like if you have any confusions or anything in the transformer architecture. So now that we have learned transformers for machine translation, like every single aspect we have learned so far, as in the self-attention, the residual connection, the layer norms and feedback layers, everything is same as for any transformer, and transformer can act as any sort of network, or rather it could be used for much more natural language processing tasks than only for machine translation. So for example, it's like, like you have textual data everywhere, like, as in like you have like multiple news articles, Wikipedias, blogs. So basically you have a lot of textual data these days. Data is like ramping up, and people call data is the new oil and sort of. So generally you might know that you might have a like a basic understanding on like deep learning models require a large amount of data, and specifically transformers require much more data because of its like complex like matrix multiplication, or rather quadratic the complexity you used to have when computing these weight matrices for query key values, and like because and you are stacking up like multiple layers. So there are going to be a lot of parameters need to be learned. So to learn more parameters, you need more data. But the problem with deep learning is like you might have to label every data you have, right? So if you start labeling all the data based on your specific task, for example, like one particular example of natural language processing is entity recognition, where you have sort of a description on an entity, and like it tries to predict what entity it is. So for that, like you might need a lot of labeled question and answer pair, or rather maybe sentence describing the entity and an entity. So basically you need to have a lot of data labeled, or maybe like sentiment analysis, where you have a sentence and you have to say whether it is positive, negative, or neutral. So those sort of things, like you might need to have access to a lot of labeled data. But like essentially labeling those data is not an easy task. It needs a lot of human manpower, and then like it is expensive in terms of like paying wages to the people who are labeling, and then like it might require some computation as well. So it's going to cost some sort of money when it comes to labeling these things. So basically the whole idea of building a general purpose transformer is like have a big transformer model, maybe like multiple transformer layers stacked together, and like a big transformer model, train it as a general purpose model, and then like adapt it to several specific tasks as required. One such example is BERT, bidirectional encoder representations from transformers. This has been introduced by Google. Basically, this will only have transformer encoders, and the idea is like you don't need to have labeled data. Without having labeled data, just with some sequences, or rather just with some text, you can learn rich representation that could model the sequence, that could have an understanding of the sequence. So we call this like self-supervised learning in deep learning, where like you don't have access to data, but like you make the model learn by itself looking at the data. So this is trained using two specific tasks called masked language modeling and next sentence prediction. We'll come back to that soon. So basically, the first one is like masked language model. So masking a language means like, let's say you have a sequence. you don't have like a specific task as machine translation, and like obviously you don't have what you call a decoder here. Like BERT will consist only of encoder. So the first objective is masked language modeling. If you have a sentence, you mask a particular token. In this case, we mask this word called brown and make the model predict that particular word. So for example, after feeding this particular masked word with the we token it with mask and say, okay, this is not this is what you have to predict. And once we input this mask token representation to the model, it will try to predict what word it could have been masked. So basically it gives a confidence of brown of 0.92%. That means like this way the model is trying to learn the underlying representation of the whole sequence. And similarly, there is a next sentence representation task. So you give two sentences, like a brown dog ran and then like Fido came home. So two sentences, and the model needs to predict whether the second sentence will come next to the first sentence, as in like if the second sentence of the input like truly like in a context like it follows the first one or not. So basically these two are like the training objectives to learn the BERT model. And this is done for numerous online data, and then the model is then being learned to understand the underlying representation of the sequence. Yeah, this is basically it. Right. So basically, once the model is pre-trained, like the pre-training is the two tasks that I have said: masked LM, which is masked language modeling, and the next sentence prediction. Once these two tasks are being extensively pre-trained, you can use the model, like the pre-trained model, and fine-tune it to several tasks you might need, like for example, name entity recognition, or maybe sentiment analysis. So the question and answering. So these sort of like different tasks, you can fine tune it, maybe like just modify some layers, or maybe modify the whole network architecture, network weights. So one way or other, you can fine tune the model to work well for your particular task. So this is basically a general, like one of the early general purpose language models. And then came generative pre-trained transformer, which is GPT. Now you might already aware of ChatGPT. This is the starting point of ChatGPT. The problem with BERT is like it does not generate new sequences, because it only comprises of only transformer encoders, right? It will give you contextual representation, but it does not generate new sequences. But rather, GPT will contain only transformer decoders, and it can generate new outputs. As in like, so the GPT has been, the size of GPT has been ramping up these days. And we might come after building a small version of GPT and see like how exactly the GPT has been progressed in the latest trends. So GPT is actually trained using a next word prediction task. So basically, if you are given with a start of a sentence, the GPT will try to predict the output here. And then like if you put like the initial outputs as the input signal, the GPT will predict the next sentence, next word. So basically GPT will only try to predict the next word at a time. That's why you see like when you ask something in ChatGPT, it will like predict the word one by one. Like you can see generate the text generation going on. So it tries to generate every sequence, every sort of word one by one, once there is an input. And it has been trained in massive scale, as in like a lot of transformer layers and a lot of self-attention hits. That brings to the end of this part of the session. We will now move on with building GPT. I hope like it's clear. I just want to see if there are any questions being asked.
There are no questions on the Menti website, Akram.
Okay, then I think we can proceed with the next part of the talk, which is essentially we'll be trying to build a small version of GPT, and after that we'll come back to see the latest advancements on GPT. I hope Abba can take over right now and proceed with the sessions.
Yes. Hello. Right. Second. Right. So hello, nice to meet everyone. So I'm Abba. I'm a PhD student at UCSD. So my main area is like chip design. So I'm not really an expert in what Gen AI, but I have done a bit of like background work and stuff. Yeah. So today, like we'll be kind of following a tutorial. So this was built by Andrej Karpathy. Okay, so you can follow his tutorial over here. So we are like most of this was taken from there. So the idea is to build the simplest version of a GPT, like step by step, and see like what are the intuition at every different point. So and get it working like somewhat working at the end, right? So that is the whole idea here. So Afham did a great job of like talking about transformers and like their history and like how they work and why they work especially, and the nuances and all. So we'll be covering pretty much similar things, like but we'll be while doing by hand. So what you might get sort of like a anchor, right? Like we are teaching the same things in two different ways. So yeah, so you can ask questions in yes. So you can ask the questions over here in menti.com. So let me put that message once again. So we'll be sort of like building a small model like iteratively, right? So we'll build one model, we'll train it, we'll do it again, like with some we add some stuff and train it, and step by step. So after every step, I would like you to ask questions based on that, and like because if you don't understand certain things, we can't proceed to the you won't understand anything afterwards, right? So right. So let's get started here. So you can see our like a material over here. So you can follow this book and you can like try it on yourself as well after this. So right. Okay. So to start, we have the let's look at the first model. So what you do is you basically go to this website, which is there in the chat and this as well. And if you click this button, it will open in Google Colab. So the people who are like absolutely new here, so Google Colab is a online sort of like interpreter. So like what you have over here is like you can type like all this code and everything. You can run it, and it will train on Google's machines, right? It will train on like Google's CPU and GPU servers and TPU as well, like if it's available. So that way, like you don't have to go through the pain of like setting up all this in your own machine and like what running all that thing. So yeah, so they have like a way of like running stuff and to teach and to learn as well. Okay, right. So let's see. Let's start with our yeah. Okay, so I don't think it's like showing up on my the screen. So like I can do like this. It's fine. All right. So All right, great. So yeah, right. So this is based on Andrej Karpathy's this YouTube like tutorial. So Andrej Karpathy is a like legend in this field. So in AI in general, like and especially in transformers and this as well. So he had like what he worked in Tesla and like he led the team in Tesla which built the self-driving the stack. So he led the team, and then like he worked in OpenAI like when they were building all this, and then he took like a 1 year break to like teach some stuff in YouTube. So which is like really fun because what like someone of that caliber like teaching stuff in YouTube. So I highly recommend you to go and like follow this tutorial. And he has like a lot of other tutorials as well. So once you get this kind of like the concept, you can follow everything else. So and yeah, let's move on. All right. So like there are so just like Afam said, there are like a few types of transformers. So one is like the encode only transformers, right? So these are the ones that extract the information to an intermediate representation. Okay. So this is from the original like attention to is all you need paper. So you have on one side you have the encoder and the decoder, two parts. And if you only have the encoder, then what you can do is something like you can do a sentiment analysis from reviews, right? If you get some text, you can get like convert that into some representation from where you can find like whether it's positive or negative or any of that. So which is usually done by like Google, Amazon, and all of them. Then you have like encoder decoder where you have both of these. So and this is used like typically for what take some information, extract the information out, and use that to generate new sequences. So this is like if you are translating from like say Spanish to English, then like you from Spanish you extract the information and then like you generate English. Okay, so that's one. Then you have decoder only. So this is where like only you have the decoder. So this is used particularly in like GPT models. So which is what we are going to do today, right? So this is to generate new sequences based on some like small inputs, right? Okay. So what is the task here? So like we are going to play with some very small data sets. So like the task here is to like to make a model to write like Shakespeare, right? So how can we do this? So for this, there is a data set called the Tiny Shakespeare. And this has like a lot of like works of Shakespeare put together, right? So the data set looks like this. Okay. So you have, yeah. And then like after that, what we'll do is like you give some starting words, and from that, it will keep on talking like Shakespeare, the model. That is what we are trying to do here, right? So here's a link to the data set, and it's a text file. So let me open that. Okay. Okay. So yeah, it's a text file. You can see input.txt. And if you just scroll down here, you can see like a lot of works of Shakespeare basically put together. All right. So now we have, so this is the data set. And the model, we are going to make like a decoder only transformer to do this. And yes, so this is the output that finally gets generated. So like after the final model, okay. So after we go through the entire iterations, so you can see it is not perfect. Okay, so like it doesn't make any sense, but you can see like it what it tries to emulate. So you can see like why proud you age, and like this is the, and you have you can see some words, and you can see the style here, like it's imitating the style. Okay, so it has learned something, but it is not perfect, right? Because it's a very toy model, tiny model, right? But the whole point is to kind of show you how to do this. So which means like you can understand what's going on inside step by step. Okay, right. So this is sort of the final model we are planning to build. So you don't have to understand any of this. I'm just showing to like to give an idea of what we are doing. So this is from the GPT-3 paper. And in this paper, you can see this architecture of what the parameters of GPT, and you can see like the number of layers, okay, which we are using, and then we have like number of heads and the dimension of head, okay, batch size. So the idea is like architecture is very similar to GPT-3. So it's more or less the same, except like some activation function and all. And the parameters of GPT are like absolutely like huge. You can see like what like 768, we are just using like say 8 or something in the middle. Okay. So you have like 12 layers and like so what the batch size is like in millions. Okay, so stuff like that. So um so in our case, it's like a very small, tiny model. So that's what I'm trying to show here. Okay, so let's start with tokenization. So tokenization, Afam talked like a bit about it. So let's go through like an example of that. So what we are doing here is basically we will do the simplest possible tokenization, right? So what is tokenization? So the idea is like you want to map certain each character or like maybe some like a group of characters or something into numbers. So the idea is like you want to convert any text because our model is going to be like, I mean, you're going to type some input text and it's going to output text, right? But the problem is like these models don't understand text at all. Okay, so why? Because you know that the operations that happen inside matrix multiplications and all this. So the operations are on numbers, right? So which means like you have to convert this text into a sequence of numbers. So to do that, the simplest possible way of doing that is like, let's say this is the vocabulary. Okay, so what is a vocabulary? That is like all the different characters in or like all the different unique types of tokens. So in this case, our simplest vocabulary is like you can say all the different characters available in the dataset. Okay. So what is our dataset? That is the tiny Shakespeare. So if you take all the characters, you can see the first character is this new line character, \n, right? So this means like you press an enter, right? Like what I think you are familiar with that. Then the second character is like a space, and then you have exclamation mark and all this. And then you have like all these capital letters, A, B, C, D, E, F, G, and all the capital letters. And then you have like this, like lowercase version of those, right? So how do we, yeah. So this is the set of all the characters that are available in the dataset. So this is the easiest way of the tokenization. So what is the size of this vocabulary? Let's say call it V, and this vocab size is 65. So you have in total, you have 65. So you have like 26 English letters, and then you have like the capital parts, and then you have all these characters. Altogether, it's 65. So to each of these, we will assign a unique number that is from 0 to 64, right? So that is our entire organization. So this again, it's like an extremely simple scheme. So if you look at this, you can have what this new line is basically 0. So whenever you see new line, the meaning of that is 0. And then if you see a space, then that is 1. Then if you see exclamation mark, that is 2. Then if you see this one, that is 3. Okay, so like that, you keep on doing it. Okay, so and Z is basically 64. Okay, so each of this is directly mapped to 0 to 64. All right. So then after that, let's see what is encoding and decoding. So the simplest encoding is like if you give a string, if you give any text, then you map that text into a set of integers, right? So if you say hello, then what you do is like you find the capital H here, and what is the number for capital H, then what is a simple E, and then simple E, then you have L, L, O, right, or something. Okay, so decoding is basically doing the opposite. So you have a character vector of integers and to map it into a string. Okay, so let's see how we can do this simple one. So using our the bigram model. So you can see, okay, so in our this one, if you click this open in Colab, it will open this model in Google Colab here. Yes. Okay. And then if you go down, you can see all the hyperparameters and stuff. And right. So we are using yeah. So we are using PyTorch. So this is a Python library to build and train these models. And then inside this, we are going to use our right. So we'll talk about this hyperparameters in a while. So over here we have our the data set, right? So what this does is to download this file from the internet. Okay, so like from this address, you do like download it to the local machine. And then over here, we are opening this this file and we are reading. So this manual seed, this part is to do what the reason to add this is like when you like every time you run something, it is going to generate like random weights, right? Like and stuff. So the model will be initialized with random weights later on. So if you like set the seed to something, then what it does is it if you set the seed to some particular value, then when you run the same thing again, like in your own machine, you will see exactly the same results, right? So that's the reason for doing this. And then if you have the right, so like we open this text file and read it into like text. So now this text contains the entire Shakespeare, this tiny Shakespeare data set, right? So it's like a massive string which has all of this data. And then what we do is we apply the set operation in Python. So the set takes the unique values, okay, and unique elements. So this what basically returns the and then you sort them out. And after sorting, this basically returns this chars is the vocabulary, right? The characters that you saw, right? So if you run like the vocabulary size is the length of this, and then we will have like two functions to mapping. Okay, so this will be like these two are dictionaries. Okay, so this dictionary, what it's doing is it's mapping a string to integer. So that is like if you yes, so if you give a character, then it like you get the actual integer, and this maps an integer to string. So it does the encoding and decoding works here. And the encoding and decoding, we define it as two functions. So these are called lambda functions. So that's like what another way of defining functions in Python. Okay, so all right. Okay, so we have the character strings. So we have like we are basically joining all of this to just see what's going on here, and then we can print these values. So when you run this, you can see it prints the vocabulary. So that is these are the all possible characters, and the total number is this. Now, if you want, like we can see the encoding and decoding functions. So that is if you say encode and so if I say yeah, so if I give a value like hello, it will print the corresponding vector, right? So this is the this is what we give to the model as the input, right? And then if you take this value and maybe give it to decode, so we'll get the same text back, hello, right? So this gives hello, and this gives the output. Okay, so this gives the vector and this gives the output. All right, so we can do this. And then this is a little bit of stuff for training. Okay, so what we have here is like we do the torch dot. So we convert this data into a tensor in torch. So tensor in torch is a multi-dimensional array. Okay, so PyTorch basically works on these tensors. So when you run it on GPU and everything, so it can't work with regular Python data types. So you convert them into torch for the rest of the purposes. Okay, so here what we are doing is we are splitting this into training and validation data. So this is a common like an approach when you are doing like any training any models. So here we are simply doing like say the first 90% of the data, 0.9 into length is the 90% of the data, is the trained data. And the last everything else, that is the last 10%, is the validation data, right? So usually we keep this separate. So you train on something and then you test on a different set of data. to see what is the error and like whether how good it's working and all. Okay. All right. So this is the data loading function. Okay. So, and this is pretty straightforward. That is, you can get the whether it's like based on train or test or something. You can, if you give train, it will give the train data, else it gets the validation data. And all it does is to like give a tuple of the input and the output. Okay. So what is the input? This X. Okay. So this is from this data, you are getting some random. Okay. So this data is the entire tensor of the entire data set. Okay. From the entire data set, you are generating a random index. And from that random index, you are taking the first T number of values. Okay. So what is T here? So T is a parameter over here, and that is, we call it the time. So that is the context length. Okay. So context length means how many tokens are we looking at a certain time. So in this case, the token is basically the each token is a character in our simple way. So how many characters we are looking at. So when you train, you want to, from this huge data set. Okay, so if you look at this massive data set, you want to randomly take, say, I don't know, like if T is 5 or something, you want to randomly take these 5 values as your input. Okay, so that is what it's doing over here, to like taking the 5 values. And then like what is Y here? So Y is taking the next a small offset by 1. Okay, so what is offset by 1? If this is the input, then the output is this. Okay, so it's offset by 1. That's what we are taking here. And why is it doing that? So the idea is like what this model does is basically, if you give like a bunch of text, say if you give say all this text, okay, so the model we are building, what it does is like it takes all of this, it looks at all of this, and it will predict the next character. Okay, so let's say like you type something like this. Okay, then it basically predicts this O. Okay, and then it will put all of this together and it will predict this R, and then it will put all of this together and it will predict E. So it can predict stuff by character, right? So because of that, we are giving like we randomly take a part of this, and that is the input, and the offset is like the output is like slightly offset from here. That's what we are doing, the input and output. All right, so this is the get batch. Okay, so now we can, before we look at the language model, okay, we will take a quick look at how tokenization is actually done. Okay, so again, like what we have is a very simple tokenization. So the real tokenization is something like this. So I can show this in this app. So, okay. Yep. Okay. So, all right. Okay. So now what you see here is the actual tokenization of GPT-4o. So this is the latest model from GPT. Okay. So which is a really powerful model. So let me type something big. So like let me type all of this. If I'm typing all of this into this, then it. Okay, you can see the output on this side. Okay. All right. So you can see the output on this side. Okay. So this is the number of tokens. So you can see this then, like in our way, what we are doing, we are basically mapping each word into the each letter into one token. This T and H and everything we map into separate tokens. But in real networks, we are actually mapping the entire word. Say that this is one token and space is this one token. Space 1 is another token, stuff like that. But then if you look at somewhere here, okay, so yeah, so each of this is one token. And in some places, like I think you have even more than, okay, Shakespeare is here, calculate is there. Mhm. Yeah, if you look at this, look at this. So this train is one token and able is another token, right? So it's able to kind of like break this word into two. So this tokenizer is like the modern tokenizers are like really very complex, and like they are able to break this in this way. So what is the advantage? The advantage is it reduces the token count, the number of tokens from this text. So if you simply convert this into characters, you have like I don't know what, probably like 500 characters or something, right? Maybe like more than that, like 1,000 characters. I don't know that many. But in if you do this, like yeah, it probably you might have like a 1,000 characters because each letter will be a token. But if you do something like this, you will get much lower, that is like 600 tokens. And you can see the actual numbers that go into GPT-4o over here. Okay. So similarly, you can go back to some older models as well. And if you see something like, I don't know, GPT-2. So this is GPT-2. And if you type some Python code in it, yeah. So if you type some Python code in it, you will see like what's going on here, right? So now this model actually takes each of the space, right? This is GPT-2, each of the space as a separate token, right? So, and this is one reason why like GPT-2 was not very good at like coding. So because like it was not the tokenizer was not very like good optimized for coding. So because of this, what happens is like these models see only a small part of the like only a certain number of tokens at a time. So then like it can't kind of like see anything beyond that, right? So if you do this kind of like a not optimized tokenization, then like the output will be like pretty like bad, like because it can't see most of the code. It can only see part of the code, right? So, but in later on, like they fix that. And if you look at I don't know GPT-4o, or if you look at even GPT-3 or something, let's say GPT-4. Okay, in GPT-4 you can see they have updated the tokenizer. So now the entire tab here becomes one token. So this is very important for Python because like the tabs implement the actual indentation. So you can see like a small tab is one token and a bigger tab is a different token over here, right? So this tokenization is pretty important and like um to see. Okay, right. So let's look at this model really quickly. So this is a very simple language model. So if you look at yeah, this is a very simple language model. So what we have in the language model is something like this. So you give one input, and looking at this one character, we predict the next character. That is this model. So this is extremely simple. So and it is, if you think about it, it's actually very dumb. Okay, because just by looking at one character, you can't kind of make any decision about the next character, right? So all this model learns is something like if you look at A, then you predict D as the next one. So if you see D, you predict like I don't know J. Okay, so that's what this model learns. So that is like extremely dumb. Like it won't help in reality. But then let's start there. So that's the simplest model. So if you give like an input which is one, then it does an encoding and converts that one character into a number. So now that number is what we call the token, right? So then that number will go through this embedding table. So this is the actual trainable layer we have, right? So, and this is the model, right? So what is this model? This embedding table is something called a learnable lookup table. Okay. So the idea of the learnable lookup table is like it is, you can think of it as like a matrix. Okay. So something like an n by n. So it's actually v by v matrix. Okay. It's a v by v matrix. So what is v? V is the vocab size, that is 65, right? So now if you give any number, if you give the number say C or something, And if you give a character C and the character's number is, I think, 15 something, then what this table does is it takes the 15th row and outputs the 15th row. Okay, it takes just the 15th row and outputs the 15th row. So this each row will have what 65. It's a 65 long vector, right? It has 65 rows, and each row is a 65 long vector, right? So when you have, if you input C, you get like a big vector 65 size. And what this vector says is what is the probability of each of this character that can be the output. Okay, so what is the probability of like each of these 65 characters to give an output? So when you train this model, what happens is the model try to learn this from the text. So that way, like during inference, when you give C that is 15 or something, then it will give a output. And then by looking at the output, we'll take the maximum probability, okay, from that output. And if the maximum probability is like, say 16 or something, then if that is D, then if you give a C, you will get a D. All right. So that is the way like this model learns. It's a very simple one, like a lookup table. Okay. What it in this table, if you give the input token, you will get the vector of output probabilities. This is what you get. And this table gets updated when you train. Okay. So this is a very simple model. And then like, so finally from there, like you do the sampling. You select which one is likely, and then you decode it and you give an output. So let's look at this model. So this is how you build the model in PyTorch. So you have to build it as a class that inherits this module class. Okay. And inside the constructor over here, we will specify any layers that we need. Okay. So this is what we have. So this is the embedding table. And you can use this nn.embedding, this from PyTorch class. So if you look at the this one, if you hover over it, it will tell you it's a simple lookup table that stores embedding. Okay. So yeah. And the size of this is vocab size into vocab size. For every possible token, what is the weights for the next token? And right. So in the forward, so like you define whatever that you want to run, like whatever outputs you want to get in this forward function, right? So within this forward function, we will see that, right. Okay. So we will see some stuff like this, like the dimensions, B, T, C and stuff. So for that, we will go back to this top. Okay. Just like I guess, I think I have it here. Yeah. So, all right. So this kind of depends on the next part as well, but like I'll mention here. So we are going to look at like our data is going to be of 3 dimensions. So that is B, T, and C. So B is the batch dimension, and T is the time dimension, and C is the channel dimension. So this also, the C is also denoted as D if you read the ChatGPT paper and all. Okay. All right. So D for dimensionality. So if you look at the time dimension, this is the most important one. That is, you have the context window, right? So what is the context window? That is a set of text you see at one time. So these decoder models are like very straightforward. So like the best part about them is they are not actually doing any sort of like, they don't remember a lot of anything. So it's like they are not remembering some stuff that was stored before or something, like you told them before or something. What they do is they just look at a certain like a size of text, and like they predict the next outputs, right? So this size of text is the context window, the number of tokens, right? So usually but if you use the GPT like 3 or 4 or something, or like all this, the decoder models, then you will actually see that what they remember, right? You can have a conversation with them, a long conversation. So you can upload like a novel or something and ask them to tell something, like all that. So the way they achieve that is to have by having a huge context window. Okay. So that way, like they can sort of they still see only like within the context window, but the actual context window is pretty big, right? So in our case, this context window is the set of tokens. Okay, what is the say what are the inputs that we are giving into this one. Okay, so what are the tokens or what are the characters that we are giving as an input, the consecutive characters, right? So this is the number of consecutive tokens we pass in. So if you look at GPT-4 Turbo or like Gemini or something, like this context window is huge. It's like 128K, or Gemini is 1 million. And now I think they are making some changes with the transformer. So like, yeah. So, right. And then if you look at the channels, so the channel dimension, so this is what we call like the dimensionality inside the model. So each channel has like different information. So each token, it kind of like expands this into multiple channels. Okay. And then like all the computation will be done with the channels. So, and finally, like but the output, you don't see the channels, right? So this is something that is hidden within the like model. All right. Okay. So yeah. Right. Each array of the transformer takes it and outputs. So then batch dimension. So batch is the B. So this batch is kind of like all independent different vectors processed at once. Okay. So which means like it doesn't matter like when you are doing inference. And the reason they do it is sort of like now like if you are running like GPT in some machine or something and some server, then they might want to take the inputs from like different users which are not related to each other, right? So you might be asking about some recipe, someone might be asking about I don't know, like some homework, and it will take all of that and put them together as one batch and put it into the same model. Okay, so they are independent from each other. So the whole point of doing this is to maximize the use of the GPU. So that way, like you can process a lot of things in parallel. So that's a batch dimension, right? But in training, this batch is useful to kind of like process a lot at the same time and then learn from that. You calculate the loss and everything and to learn. So during inference, you can set the batch to like a 1. All right. So these are the 3 BTC dimensions. So if you go back to the code here, then you have this is the this is the model. So what we do is the model does only one thing. It basically within the embedding table, it passes the input. The input, let's call it index. Okay, so this index is a B comma T matrix, right? So that makes sense, right? The B is the number of different different inputs you can put together. And then T is the set of the context window size. That is how many consecutive elements you are giving together. So initially for bigram model, the T is equal to 1. Okay, so it is we are giving 1 character and getting 1 character. Okay, so yeah, and this is the output from here. And then what we do is we pass this logits into a loss function, the cross entropy loss. Okay, so this cross entropy is like a popular function which we use in a lot in different parts of machine learning. So this is the function. You basically have a ground truth, that is the TI, and then you have the output from the model, that is the YI, and you sort of like you pass this into this and you sum up. So similarly, you can right. So yeah, then so that way like you calculate how much error there is. Okay, so if the output is exactly correct, then you don't have any error. But if the output is like slightly different from what you expected, then like you have some error, right? So you calculate this loss and you try to minimize this loss. That is the idea. Okay, so this generate is a simple function that basically applies this applies a softmax to the output. Okay, and so yeah, so it applies it runs this model, it applies softmax, and then using this what it finds the maximum it finds the element which has the maximum value, and from that you calculate you find which is the output, which index is the output. Okay, so that is a pretty simple way of to generate outputs. So then you can build this model using model equals this bigram model over here, and then so you can do model.to device. So this way you can put it on a GPU or you can put it on a CPU or something. So currently I have put it on the CPU. You can change this to GPU to run faster, right? If you have a GPU. And this is the function to estimate the loss. So, and then like you have an optimizer called the Adam W. So there are like different different optimizers. You have Adam optimizer, and you have variants of that. And so these are all used to to minimize the loss. Okay. So and to update the values, right? Like in the weight values from the loss. So that's how you do the training, right? So this is the training part. So again, this is pretty simple. Every once in a while, you print the output in here. Okay, so this prints the output, and then you get a batch of inputs, and then you evaluate the loss, and you run the optimizer. Okay, and optimizer.step. So if in every step, it updates the weights of the model. So here the weights are pretty simple. It is just an embedding table, right? Just a one matrix. That is everything. The whole model is just one matrix. You just keep updating this matrix again and again, right? And finally, this is the inference. And in inference, if you run this context, if you take so here we have to give some input to this model. So for the input, what we are doing is I'm just putting this torch.zeros. Okay. So this way you are starting with this n as a seed, and then you keep generating the output, and we look at this. So instead, we can actually put any value as the input in here, right? It doesn't have to be a 0. You can type something and it will generate. Now, if you look at this is actually pretty shitty, like even after training all that. Okay. So yes. So we are doing the training here, and then even after that. Okay. But then you can see that it is learning some patterns. Like for example, just like Shakespeare, it is doing something like this, and it puts a colon, and after the colon, okay. So now you see after the colon, there is a new line, right? So now this model has learned by itself. So because it is only looking at one element and predicting the output, it just looks at this column and says whenever you have a column, okay, the most likely output is a new line. So that is literally the only thing this model has learned, right? So yes, okay. So we have a output from from the model like this. So now obviously this is not a great model, but then what can we expect? We are only looking at only one input and output, right? So if we look at the next one, so next step of this is we are going to add the linear layer and the positional embedding. So okay, so if I add so we'll improve this model. We'll add some parts to it. Okay. So the first one is the positional embedding. Okay. So the positional embedding, the reason for this is so just like Afam told, now what we did so far is we just had an embedding table, or if you have yeah, so we had an embedding label which kind of learn something. But then if you give t number of tokens, so if you give a word hello, the model need to know that H is the first letter, E is the second letter, L is the third letter somehow, right? Because if it is just a vector, it doesn't know which is and when you do a multiplication and all, it doesn't know that. So for that, what we do is we put this positional embedding. So this is a similar to the embedding table that we put previously. So it's learned again, it is learned, and then it is going to generate for the entire context length, that is from the T context length, it is going to map it into C, that is the intermediate what the channels or the dimensionality, right? And then we add the what comes from the token embedding and the position embedding together, right? So this position embedding, the input to the position embedding is 0, 1, 2, 3, up to T minus 1, right? So T is the context window size. So if it is 8, then 0, 1, 2, up to 7. Okay. So from here we get the positional embedding, and then from here we get the total embedding, token embedding. We add them together. So by adding them together, we are kind of combining them. So we are telling the model, okay, H is the 0 and E is the first one, L is the second one. So like that. So if you give an input as hello. All right. So what this, yeah. So this embedding table is basically like mapping this like a one mapping this one, say, number into this C number of C channels. Okay, so this is also learned, and then you combine by addition. And here the key part of the model is now it's a linear layer. So linear layer is we call the dense layer. So if you have done like MNIST or something, you might have like if you work with MNIST data set, the very simple like neural network you'll be building is something like a couple of like dense layers, right? So that's what we will have. And then this dense layer will be like mapping this BTC into BTV. Okay, so BTC is the tensor size. So batch, B is for batch, which are independent stuff. And T is the token, that is the number of characters we give at a time. C is the intermediate dimensionality. And from here we map it into V, which is the like vocabulary size, right? So let's see how that is done. Okay, so let's see how that is done. So if you look at the if you go down, you can see the, so if you open this in Colab, all right. Okay, so now we are like we are setting 32 as the batch size for training, and then T is 1. That is like we are still looking at 1 and like finding the output and all. And then you have 32 is the intermediate size, right? So if we keep going down, like the main changes we have made here are we have added a head here. That is the like linear layer, right? So we have added a new linear layer, so which is doing the actual processing. So also we have the token embedding table and the position embedding table. So both of these are nn.embedding, right? So the token embedding maps from the vocab size, that is like 65. It's a table of 65 rows and the C number of columns. Okay, and then this position embedding table is it maps from I guess from B to C. Should be T, I guess. It should be T. So it maps from T to C. Okay. All right. So I will update this later. So yeah, and then we have the actual like the actual layer here. Later on, we have our token embedding here. So this is during the forward function. When you run the model, it every token is cast into like its own representation, and this is learned. This transformation is learned. Then this is also learned. You add them together into the input, and this is passed through this one linear layer in here, right? And then you run through the whole thing, and like you generate the same thing. Okay, so everything else is similar. So if you run this, so now you can see that it has like learned a little bit. Okay, so it is not a lot different. It is still pretty like incomprehensible. Okay, but then there are like something like sentences, and then you have like what you see like it's a little different from previous one. All right, so how can we make this even better? Okay, it's pretty bad. So what do we need to make this better? So that's where we have the attention is all you need, right? So you're going to add like attention to this. That is the self-attention mechanism, right? So if you go back to our example here, okay. So the next one is the self-attention mechanism, okay. So we will see a little bit about it before looking at the code. So Afam talked a lot about this. So I will quickly summarize all that. So what we have here is let's say this CI is the input channels or like the input dimensionality, and CO is the output. Okay, so usually these two are same. I'm just putting like different numbers to show these matrix multiplications, what is going on inside. So the first thing we do is like you have the three matrices, which are like learned matrices. So these are three linear layers. So and these weights are learned from here, and then you pass this input to each of them. You do a matrix multiplication and get the output, right? So you are basically doing a linear transformation from the input to through these three different ways, right? And what you get as the output are the Q, K, and V, the query, key, and value. So these are projections of X. Okay. So what these matrices do is to project X in three different ways, right? So you first do that, all right? Then afterwards, you have like a series of operations, which we will look like later on. So the first operation is to do you do a matrix multiplication between Q and K. So this is where you get the power of the transformers, because the operations after this over here are sort of data dependent. So you are like kind of like looking like the data is processed with the data itself. So unlike say convolution layers, it is sort of like you give an input and it's transformed, and you get an output. Okay. So, but here you have like the two different projections of input, you combine them together. Okay. And then like we do a bunch of operations. We look step by step. Right. So let's see a quick intuition of these things. So one is each of these Q, K, and V are three different versions of their raw data. Right. So three different projections, and you can think of them as three different versions of the data. So what is query and what is key and what is value? Okay. So query, you can think of it as what I am looking for. So you can see like maybe the vector or the token is saying something like I am a vowel in this position 8 or something, and I'm looking for consonants up to position 4. Okay. So each of these so you can see each of these T. Okay, so T is the context window. That is basically the number of tokens, number of characters you pass at the same time. So let's say if you pass say 4 values together. Okay, so if you pass 4, or like if you pass T number of tokens at the same time. Okay, so you can think of it as a sentence, or like you can think of it as a word or something like that. Okay, a set of text, and each of this will be looking at other tokens. Okay, so in the query vector, like when you project this set of tokens into query, what the query will be doing is basically the query, each of this token, each of the character in the query will be searching for other other tokens which have like relevant information. Okay. Okay. So yes. All right. So you have in the query, like each token will be looking for more information. So in the key, you have the actual information. So each of the token will have some information about itself. It will be like I am the consonant in position 3 or something like that. So then the value vector is basically like which we get at the end is something like some more information about itself. Okay. So the first thing we do over here is to do we do a dot product between these two, the query and the key. So which we look at next. Yeah. So we will do the Q into KT, right? This is the transpose operation. So we do like between Q and K, we do a dot product. And when you do a dot product between Q and K, what we are doing, what you get at the end is one matrix. And this matrix will be pretty sparse. Okay. So what it does is like now each of these tokens are searching for something, and each of these tokens are also giving out some information about themselves. And when you do a dot product between them, if any of these tokens find some information that they are looking for in some particular token, then at their particular intersection, the value will be high, right? So like in that area, like the value will be high, and in other places, the value will be low. Okay. So a good way of thinking of this is like if you are giving a value, if you are giving a sentence, something like um, say like like this guy was doing this and this, and he like went out and did something else. So like let's say it's a sentence. Then if you say the word he represents this guy, right? So inside the transformer, this he will be looking for like what it means, and it will match with the token that is representing this guy's name in the same sentence. Okay, so that is one way of like understanding this. All right. So then after that we have the so after you find all these affinities, and then we divide it by the square root of C node, C out. So that is the dimensionality. So to normalize this, and then we pass it through softmax. So softmax highlights the maximized affinities. Okay, and this suppresses the other affinities. So that way you get like a sparse, this matrix will be a sparse matrix of which keys have found which queries. Okay, this other way around, which queries have found which keys, right? So that's what you get in this one. So what exactly is softmax? So softmax is like this is the function. So what it does is if you pass this as the input, then the output will look something like this. Okay, so you can see over here like this, like you have 1.3, 5.1, 2.2, 0.7, 1.1, all that. So this 5.1 is the maximum one, right? So this maximum one will be boosted. So finally you have like 0.9, and everything else will be suppressed. So this gets 0.02, 0.05, 0.01. Okay, so here you have like a big peak. So that's what softmax does. And it will make sure like everything, the sum of everything is equal to 1 as well. Okay, so which is good for learning. And if you go to the next part from here, then after this, we apply the triangular mask. Okay, so yeah, so we apply the triangular mask. So the idea of the triangular mask is to have something like this. Okay, so this is called the lower triangular matrix. Okay, so if you do this, what happens is like we are basically making everything in this part. So if it's a 3x3 matrix, in these places we are making them 0, and everything else we have values, right? So the reason for applying this sort of a mask is to make sure each node can only look at the information. Okay, only search for the information and everything to itself and the past. So it can't search for the information in the future, right? So because if you have some sort of a token, like some word here, okay, so one word can't look at the future tokens. It can only look at the past tokens to get the information. Okay, so we use this in decoder only models. So, but if you're like using some encoder decoder, like if you're doing translation, that doesn't make sense. So we don't use the triangular mask. That is like if you're translating from English to Spanish or something, you have to look at the entire English sentence to make every token of the output sentence. So there you don't need this. But in GPT, where like you type some question and it types an answer, to train that model, you have to make sure like by looking at the first few words, you have to guess the next word. You can't look at the words that come after that, right? So for this, we use a small mathematical trick. Okay, so the mathematical trick is something like this. So let me show that over here. It's the same thing. So we can use it over here. So we do the weight. Let me show it here then. Okay. So in this model, everything else is same. Only thing is we are adding a self-attention model weights here, right? So here you can see the key, query, and value are like 3 linear layers, okay, with CI and CO, which will be same. And we have to register a buffer called the triangular matrix, okay, for PyTorch to do the work. And then, right. So here these K and Q are the key and query projections, right? So we pass them through it, and they are the projections. And then if you look at this weight, this is the affinities. Okay, weight equals Q into K. The at is the matrix multiplication in PyTorch and NumPy and all, right? So you do the matrix multiplication between them, and you get the output. And then you do this one, and then we have the okay. What we do is that we do a masked fill, that is using this lower triangular matrix. Wherever this lower triangular matrix is 0, so where is it 0? It is 0 in the upper triangular part, right? Like where I showed here. So it will be 0 in these parts. So wherever it is 0, we replace that with infinity, minus infinity. Okay. So it's a small mathematical trick. So what it does is, like when you run a softmax in the next step, okay, all these minus infinities will become 0 automatically, right? So because we are already using softmax anyway to do the to normalize this. So this is a small trick to kind of like get what we want. Okay. So that's the idea of this. All right. So, and after this, we have right. Then finally, we have the value multiplication. That is, so the value vector is more information that it's really willing to provide. So, and when you do the affinities into value, so you are sort of bringing all the information back to the each node. So each node is kind of like looking for all the information in the previous one. They found the information like by like searching, and after finding it in all of the information, you bring it back to yourself, right? So you like get all the information back into yourself. So for that, we multiply it with value, and like that is what we use as the output. Okay. So this is similar to filtering. Okay. So the filtering is like if you're if you have a set of values, then you average the nearby values and put them here. All right. So if you're in ENDC, you know like the filtering stuff, right? So right, and it's similar to that, right? But here again, like in average filter, you have like a bunch of values which are constants. But in here, in this matrix, the values are learned, right? So that part is also learned. And after you do all this, finally you will have a y, which is BT-CO. Okay, so it's similar to the same shape as input, right? Okay, so right, so there are actually other modern types of attention. So one is like in encoder, you don't have a triangular mask, and just like in translation. And what we are looking is self-attention, where Q, K, and V are coming from the same input, right? And then another way of like doing it is cross-attention, where the Q is coming from one, and the K and V are coming from a different one. Okay, so it's coming from the K and V are coming from the encoder, and this coming from the decoder. Okay, so this is also used in translation, right? So this is one way of doing it. Okay, so if we add the attention to our model, we can see the results improve a little bit. Okay, yeah. So now we have put all of this together. Okay, and you can see that I'm creating this head here. Okay, as the SA head, self-attention head. Okay, and then I'm passing the information from after doing this token like embedding. I'm passing it into the self-attention, and after that, I'm passing it through the head, like the linear layer to get our output. Okay, so if you run like the training and all, we finally get the output here. Okay, and so this output, like it looks similar, but there's like a little bit improvement. Okay, not significant improvement, right? So for this, like now we have to add more complexity. So the next step of doing this is the parallelization, right? Like you want to, but you want to get a lot of different information in parallel. So for this, we use the multi-head self-attention. Okay, so which is the same attention, but like so attention is what you saw previously, right? That is the entire thing is the attention mechanism, right? So we pass this attention mechanism, but now you copy that into like say 0, 1, 2 up to like h different heads. Okay, so number of heads is h. So like a key part you see here is all of these attention heads are getting the same input. Okay, the exact input you are giving into all of them, but the outputs are now what you get from the output, that is the CO. Okay, so that is the say output channels, you can say. So the CO is h times smaller. Okay, so if the CI is what 32 and you have like 4 heads, then the output is each of them will output 8 channels. Okay, they are not outputting like 32 channels, they are outputting 8 channels, and you just concatenate all of them together into 132 channel, right? So 132 sort of like a vector. So the reason for this is all of these attention heads are looking at different stuff. Okay, so this way you can kind of like extract more information, even more information. So for an example, each head is looking at different things. Some head will look at sentiment, some head will look at whether it's active or passive voice, and others will look at some other information from the same text. And then you put everything together into one big vector, one bit matrix, and then you pass it to the next, like you send it through a projection layer, another linear layer, and you pass it as output. Okay. So by doing this, we can like we can extract even more information, right, from there. So now we have a new parameter called h. So h is the number of attention hits, right? Okay. So if you go down here, like if you can see how we have implemented that. So you can see in the model and in the attention head. Oh, no, this is the okay. So here we have implemented the multiple heads. Okay. So this is a list of modules. Okay. And each module's input is C, which we have, and then output is C by H, C divided by H. Okay, for range of these modules. And then after that, we pass through the feed forward layer. Okay, so which we'll look at here. Okay, so this feed forward neural network is the right. So this is a very simple neural network which can have any activation function. So just like Afam said, the most common one is GELU, but here we can use ReLU. So ReLU is the like very basic one. So and what is a feed-forward network? It is a very simple dense network. You have 2 linear layers. Within that, you have a activation, right? So the purpose of this is the model can think about what it learned through the MHSA, okay, through the multi-head self-attention. So from this, you find information. You basically find a lot of information, and you are sending that information. But then, like over here, this is not data dependent. So here, what it's doing is it's doing some thinking, like it's analyzing the data that you collected previously, right? And then you pass it through the final linear layer and give it out, like just like before, right? If you do that, then what you get is what the output is like this. Okay, so now you can see what it's sort of you can see more structure in the output. Okay, I something say will, and you have like say you can see like couple of words and stuff like that. So it is learning something, right? So right, and the next one from here is the like the residual connections, right? So before we go there, we will check any questions up to now. Right. So I don't see any questions on Mentimeter, I guess. All right. So yeah, there's a question here with the encoder decoder model. Yes. So there's a question about the encoder decoder model. I will let Afam answer it. So he's like a better expert on this. And then we have the question about the instead of text data set, can we use CSV or data table data to do this task? Okay, so the only requirement here is for a transformer is that the data should have some sort of a sequence information, right? So if it is like a meaningful sequence, you can use that. So if you have like say I don't know stock market data or something, then as a CSV file, you can still use that, right? So and that is kind of the like sort of the power of transformers. So they have this innate idea of multimodality. So you can basically chop up any data. Okay, it doesn't have to be say yeah, it doesn't have to be like text. It can be images. It can be like anything else, like audio and everything. So you can chop up any data and you can mark it through like projection. You can mark position encoding and stuff, and you can put them together and you can make the model learn all of it together at the same time. Okay. So unless if it is some discrete, complete discrete data, like if you say something like the height of the students in a particular class, so in a CSV table, okay. So I don't think it's going to learn anything particular from that because the data is not sequential, right? If you have different guys will have different heights, and that doesn't correspond. So if it is like some prices over time or stuff like that, you can make it learn. All right. So next one is the residual connections. So this is so Afam touched upon it as well. So this is the key idea for this is when a model gets deeper. Okay, when you have like too many layers, then the way that gradients are calculated. So like how the model is trained is basically you calculate the error at the output. Okay, and from the error you update each weights like using backpropagation, right? So this what is backpropagation? This is like the chain rule in calculus. Okay, so you kind of like find the error like here, and based on the error, you calculate how much this weight should change. Okay, and then from that like you calculate how much the previous like one should change. Okay, so like that like you keep on like iteratively doing that until the from up to the beginning, right? So when you do this, what happens is the gradients becomes like if the model is too deep, when you have too many layers from the back to front, like it takes a long time or so many different training epochs for the gradient to like propagate or like to make any changes in the first few layers, right? Why? Because they are far away from the output, right? So because of this, for a very long time, the first few layers will not learn anything and they'll be producing gibberish. So this kind of like affects the training process, right? So then to how do you solve this problem? So this is like a very old problem. And so when in AI, when you say something is old, it's probably like, I mean, like 10 years old, right? Not like 100 years old or something. So, and the ResNet paper, what it introduced the idea of like these residual connections. The idea is like in the forward path, what you do is you take an input and you simply pass it across and add it here, and you pass it across and edit here, right? The input. So if you do this, what happens is when you train, the gradient from here, okay, can be directly applied to the gradient here. So this gradient is it takes the data from here and here, from both paths. So that way, like now the gradient can reach to the top layers quite fast. And that way, like in the first few epochs, you can change the weights in the first layers, and that way you can learn like really fast. That is the whole idea, right? So to solve this problem, like resonance are used in the essay paper, and this way you kind of like use the skip connections to like jump over things. So in transformers, they use the same idea. So the skip connections are added across the MHSA and across the feed forward layer. Okay. So if you look at our code, it's somewhere here, neural networks. So yeah, so we have like here we have broken this head into its own module just like before, and multi-head self-attention, it's its own module, right? Where we are doing like multiple heads. And then inside here, we have the transformer, like we make a new block called the transformer block. And in this transformer block, we have the yes, okay. So here we are simply adding some the residual connections. That is, we first pass it through the self-attention layer, the multi-head self-attention. Okay, and this X is the input X, and we are adding them and like passing it as the output, and then we are using that into the feed-forward layer, which is doing the thinking, and then you like again you add it to the connection and pass it out. Okay, right. And then you have the model, you simply build it with that. Here I have put 3 block layers like this. And then when you train it with that, let's see. Yeah. When you train with that, so this is the output. And there's a slight change from there. So from there, we'll go to the next step, that is having multiple blocks. So which also we just did. So the idea is to, like, previously we had only one image, say like one attention block, and then after that you had only one feed forward layer. So now we abstract this into a block, and you can put many of the blocks, like one after the other, right? So now we are making this model deeper, right? So to make it, and having this residual connection actually helps with making it deeper as well, right? So that's what we have done here, and this is the output, right? So right. So as the final steps, we are going to add some stuff that helps with training. Okay. So what we are going to do here is so the first one is like layer norms. Okay. So layer norm is similar to batch norm in CNNs. So if you are doing, like, if you have done some like convolutional neural networks in the past, then we use batch norm layers. So the reason for that is to do training easily. So the reason for that is, like, the weights are initialized in a normal distribution at the beginning, right? So if the if the inputs and outputs change like a lot for like every batch during training, then you are going to, like, the model will have a hard time training. So it will take like a lot of epochs, right? So instead, like, we normalize the input to each layer using like batch norm or something. So that way it has a similar distribution for every um, iteration. So when you do that, it becomes much easier, right? Like the training becomes much faster because the weights can update themselves. Like they don't have to change too much. They can change only a little bit, right? So if the distribution stays the same. So, and this helps training the deeper networks, right? So layer norms are similar to batch norm, but the difference is, like, it is applied along the C dimension. So the C dimension is the one that contains like different information about the same token, right? So like it is the layer norm is applied along C, and all right. So these are the right. So this is the equation for layer norm, and this gamma and beta. So this gamma and beta are trainable scalars. So like when you do the training, they actually, like, this gets updated as well. And during inference, we use that thing as it is. And this E is the mean, and this is the variance, right, of the of a set of the inputs, right? So nowadays we are adding this to the input. So like we'll put over here. So right. So that is one change. And the second change is like adding dropout layers. So dropout layers, what they do is, like, whenever you do training, they randomly set a certain percentage of values to 0. Okay. So like inputs to themselves. So they just like randomly disable some values. So this helps the model to be robust. So if you don't have this, what they do is like the model will kind of depend on certain neurons too much. Okay. So by using these dropouts and randomly disabling it every time, the model kind of learns to use all its neurons in a proper way, right? So here we use the dropouts to affinities to the softmax at the end of attention and at the end of each block also. So during inference, these have no effect. In the when you are doing the inference, you simply disable the dropouts. So that's what we do, right? So this is just for training. So yeah. Yeah. So we set the hyperparameter as the dropout percentage, that is 0.2. And then if we pass it, we add it at the end of every feed forward layer here. And yeah, okay. So all right. So if you run the whole model and if you run the training and like inference, so this is what like we get from this model, right? So this is the sort of the final version after putting all this together. And you can see like it is actually doing something. Like it has like one person is talking and then there's a different person talking. Okay. And the style is something similar to Shakespeare, but even then it's very incomprehensible, right? So the reason for that is this is still like a very small model. So if you want to try like a bigger version of this, then you can enable this final hyperparameters. So you can see these parameters are very small. So the T is 8. So it is only looking at 8 characters to produce the next character. Okay, so that is very like that doesn't like it's not even a word, right? It's like part of the word, right? So you can increase it to 256. So then now it's kind of more robust. And then you have the C is the channel, and you like you increase it to like 64 into 6 or something. Okay. And you can have 6 different layers, and you can so this is like the final hyperparameters. But this takes like forever to train in Colab. So on my laptop it took like 30 minutes to train with this. So if you do that, then you can get the sort of like the final output. Okay. So if you look at the final output, it looks something like this. And you can see like some sentences here, like provoker, you got my horror lord or something, and you must bitten like it great. So it has learned something to talk about like Shakespeare, right? You see Brutus, okay? Let us roam, we put and all this. So yeah, so this is what you finally get from like this model, okay? So what we have over here is like in GPT 3 paper, you have this the T is like quite big, so that's like 2048. So not even so we were what I showed was like 8, and this is T is equal to 256, and in GPT the T is equal to like 2048, and then you have like the different values for the parameters are over here. So like if you look at the recent kind of work and like all the GPT and like all the papers and everything, the model has not changed like too much. So I think they are changing it a bit with Gemini and like GPT-4o and like all that. And like I think Affoman talk about it. But until very recently, this model has stayed the same for like 6 years. Okay, the whole architecture. Okay, so it is a very robust architecture. And like, but what has changed like with every because we know that definitely like GPT-4 is way better than GPT-3 and all that. So what has changed is basically the number of parameters. So they have made the model bigger and bigger and bigger. And when you have these massive giant models, the hardest problem is training, right? So you can't train them on like GPUs, simple GPUs. So usually they run it on like massive GPU farms. So, and when you train it on these GPU farms, there are the ways of like distributing this training on different GPUs, right? So, and then sometimes these GPUs fail, and like then you have to kind of like come out of that and like that. So today, like most of this, like every iteration is sort of like an engineering challenge of how do you train an even bigger model. Okay, so and yeah, so it's basically like what you learned here, like of what you learned here of how to build like an nano GPT. So this is this is the same model that is used in GPT 3 and 4 and all. Okay, so same architecture. The only difference is like they have way more GPUs than you. Okay, so and like there are a few differences of like activation function and everything, but like the major difference is that. Okay, all right. So let's see. All right. So Afam has answered this question here. All right. Okay. So I think I'll hand it back to Afam so he can continue and like hopefully he can say like what are the drawbacks in this toy model and what are the changes that like we have in the today's models. Thank you. Thank you so much.
Hi everyone, welcome back. Thanks, Abba. So I will take it on from here. I hope you all can see the screen. So basically, Abba has touched upon building a smaller version of GPT and talked about how you can like have a hands-on experience. You can try it yourself and play around yourself with changing the parameters and stuff, and also maybe like training with some sort of new data and exploring it yourself. The major challenge in that particular model is basically it's very small scale. It does not have a lot of data to train, and it does not have a lot of parameters to learn around. So there is a challenge on adapting to new scenario and like generating new sequence in that scenario. So basically, what people have come across, as in like what people have built these days, is called a large language model, which I will briefly touch upon and like talked about the advancements, challenges, and things that you can do, the applications and sort of. And I'll make sure I'll finish it quickly. Maybe like you guys might be very hungry by now, I guess. So the large language models, which we briefly call LLMs, are going to be the topic for the next couple of minutes. So basically, LLMs are massive transformers. That's sort of the very high level idea of seeing what LLMs are. Massive transformers stacked upon each other, without any modifications, without much modifications to the fundamental blocks, and also without much modification to the learning, the task of learning the next word prediction as well. So we have seen that soon after the advent of transformers in 2017, the BERT was introduced that uses only transformer encoders, and then we know GPT was introduced that was using only transformer decoders. So Abba has like comprehensively explained on building a GPT and like what are the functions of GPT. But we know for sure GPT, there has been a massive upscaling happened around the early 2020s on the number of parameters that were used for GPTs. So basically, you can see in the diagram on the left side. So GPT-2 is somewhere here, like early 2019. And you could see the jump to GPT-3 is huge, as in like really huge, more than hundreds of times. So the number of parameters went up to 175 billion for a neural network model. So that actually made sense for all of this realistic natural language generation. I mean, like you could use GPT-3 to generate much more sensible natural languages compared to what you have seen in the simple small scale GPTs during Abbas session. So even after that, recently GPT-4 has been released, and it's like around 1 trillion parameters, and it's still going upwards. So people are like scaling up massively, and without changing much of the fundamental blocks and without changing a lot of the learning parameters. Obviously, there are small changes in the normalization and in maybe the activation functions and so on and so forth. But still, the basic fundamental aspect of the transform architectures remain the same, and it just scaling up the number of parameters, making the deep learning, making the large language models work so well in a diverse range of natural language processing tasks. It's not also just the parameters, but also the diversity of the training data set. You could say this is one of the examples of one of the papers released by OpenAI, which talks about how scaling can improve the deep learning models, especially in transformers. As you know, transformers have this special ability of this residual connections. So these residual connections will have the information flow, even though for very deep neural networks, very deep transform architectures. So you could see this particular data set size, like whenever the data set size increases, the test loss tend to decrease, and it's linear, it's not converging as well. So which means like we could go on a little bit further and increase the data set size, and we could reduce the test loss to a certain point as well. And also with parameters, increasing the number of parameters, we are reaching like 10 to the power 9s now, with like more than 10 to the power 9s, like with trillion parameters, and it's still reducing the test loss, which means like we are not still converging to a point that increasing the data sets size or parameter size doesn't make sense, which will obviously, there will be a certain point where the convergence will happen, where like even increasing parameters or data set size will not do such improvements. But as of now, people have found out scaling is increasing. And also diversifying the data set is so important for general purpose LLMs. So basically, you have seen with Abbas presentation, or the workflow, that we are training the GPT model basically to work as a, say, Shakespeare, but it does not adapt to, or rather it does not work for other language tasks. But what these LLMs does is like they train on massive diverse range of data to maybe like Wikipedia's blog post, even coding, GitHub coding, and so on and so forth. With those diverse amount of training data, what they're capable of doing is like they can do multiple tasks all at once, like rather than depending on a very simple single task. We'll have a very quick look at that. So what this makes possible is like from GPT-2 to GPT-3, they have introduced something called prompt engineering. So before GPT-3, maybe like we could call GPT-3 as an LLM, and like before LLMs, what happened is for fine tuning, basically like if you train a big model to adapt that big model to a specific task, what you have to do is you have to do the fine tuning yourself. Especially if the model is huge, fine tuning a model itself it's going to consume a lot of energy, and like it's going to consume a lot of compute. For example, like if you want to translate something to French, like if you have a big model, and like you have to give some examples to tune the model for translation, like you have to update the gradients of the model every time you provide some examples to make sure that model learns some sort of like understanding of the English to French comparison. And then only once you give what's the French translation to cheese, it will try to provide the answer. But what GPT-3 has done is they introduced something called prompt engineering, where it works in three different settings called zero shot, one shot, and few shot. Zero shot is an example. So there is so basically prompting is something like you tell what the model to do. You sort of like even using chat GPT, you can tell, okay, translate this English to French, and okay, or maybe like the task, like you are simplifying the task to an LLM, that's like a prompt. So basically you are describing in zero shot, you are describing the task, translate English to French, and you are directly giving cheese and what's the translation. It will look at all the knowledge of it's been trained on, and it will try to translate it to French. One shot is giving one example rather than just asking what it is, like just to giving an in context example, maybe translate an English to French, but you're just giving an example that see auto translate it to something in French, and then like asking what is cheese. And the other thing is few shot means like you are giving like some more in context examples to make sure that the model, the LLM understands the task pretty much very well. So you give some examples. So basically at this phase, like at this phase of this prompting mechanism, the GPT-3 or the large language model is never been fine-tuned, which means like it's not, the gradients are not updated, which is in opposition to the one we have been doing previous to the GPT-3s. So there are like pros and cons of these mechanisms, like few shot, one shot, and zero shot, like, and some works in some settings and some doesn't work in some setting. But generally like few shot works in most of the natural language tasks where you have to give some in context examples. Like if you have a question to answer, if you give like some sort of question answer pairs previously, it will try to understand the context of the task you are referring to, and then it will try to answer that. So that is basically the prompt engineering, which is an advancement that LLMs have brought in. If you see the massive like the massive ramping up in like the LLMs these days, large language models, like every big company has involved in building a large language model. For example, Google has built Pamela, Lambda, and then like they are now building Gemini as well. And then like Meta has this big llama models that does this on OpenAI. Like without no surprise, they have been building GPT-4, and recently they have released GPT-4o as well. So similar to that, there have been like huge competition among companies on building like large language models to get better performance on natural language processing tasks. The interesting thing is like not all these the large language models are open sourced, which means like you cannot just download the model and use it for own purposes. Some models are like obviously open source. For example, Meta's Llama models are open source. You can directly download and use it for your specific tasks. But like for example, OpenAI's GPT models are not open sourced. It's closed source, but you can use their APIs to build your specific web applications as well. So these are some of the examples of the large language models out there. One of the interesting things that is used in building these large language models is we call RLHF, which is like human feedback, like LLMs with human feedback. Basically, LLMs can generate a lot of stuffs, like which could be like we'll see in the challenges and ethical considerations of LLMs in a while. But LLMs have this massive problem of biasing towards a specific, and like it also has this problem of like giving wrong answers in a very confident manner. Like you could see like in the initial talk by Sadeep, like explaining who Sadeep is, but like the major problem there is like it is very confident on that answer, which is wrong. So basically what the people building LLMs try to do is like they try to include human feedback, where humans are trying to rank the outputs from LLMs and give feedback from the give rewards if the LLM predicts the right answer or rather much more best answer, or it punishes the model for bad answers, which means the LLMs are further fine-tuned with a human in the loop. For example, ChatGPT is trained in such a way, and GPT-4 is trained in such a way to give much like a neutral and also common sense and human centric answers possible, because like there is a human in the feedback. So this is an interesting technology that been used these days, using human in the loop and updating the LLMs, overcoming some of the weaknesses and considerations, ethical considerations that been discussed for LLMs. And another interesting thing is you can't, like as I said, you can't fine tune the whole LLMs because it's massive. Like fine tuning 175 billion parameter model is huge. It's not easy. So basically, people have come up with like parameter efficient fine tuning, how you can like do some tunings or tips and tricks to tune only efficiently tune the parameters. Well, three examples are prompt tuning, adapters, and LoRa. I'll just touch upon these things. Prompt tuning is basically training a model that could generate more sort of that could generate prompts that could give you a correct answer without training the LLM, without modifying the LLM. You just make sure you are giving the correct prompt. So this prompt tuning models learns a correct prompt for the pre-trained models. So, and adapters have this very lightweighted models. It could be transformers or it could be linear layers that is fed to the transformers. Like you see, this is a transformer layer, and like you feed transformer adapter models in between them. This could be a transformer layer or maybe. So this is basically an MLP where like you have feed forward models, or it could be like a simple transformer models as well. So these adapters, while fine tuning, you tune only the adapter to make sure that works for a specific task rather than the whole model. So this is one of the interesting ideas. And this LoRa is also very popular parameter efficient fine tuning method these days, where you just keep the pre-trained weights of the large language model as itself, but you train some sort of low dimensional matrices, learnable matrices, to make sure that works well for your specific task. So these are some of the examples I wanted to touch upon on how you can make your LLMs work on a specific data set. For example, I mean, LLMs are generally trained on massive data set. They are not specifically trained for a specific task. But if you want a model that should work on a specific task, you have to tune it in such a way that it could work for a specific task. I just wanted to like talk about some of the interesting applications of LLMs as well. I mean, like you might been aware of a lot of these things. Grammarly is like helping people to correct the spellings or maybe correct the grammars. And ChatGPT, we all know that. And Replica is sort of a mental health assistant. And Bloomberg GPT is like sort of a large language model for finance, like finance-based conversation. And also it helps in like the stock trading as well, how exactly it could analyze the stock market currently right now in the context of finance. Lin is a Sri Lankan platform. This is sort of a customer service solution that's a solution that's been introduced. So it uses ChatGPT API as well. So there have been several applications in the context these days, and business as well. So concern where like the models can sort of, I mean, the training data, we don't know how exactly it's. So specifically the stereotypes or gender, racial, cultural biases as well. And also misinformation, as I told you, like one of the major problems in LLMs is like it conveys the wrong answer very confidently. So which means it gives us the false information. So it's really hard to it also depends on data because it gathered data from a lot of sources, and it means like data might be true and might be false. So there should be a curation needed in pre-processing the data to be fed to the LLMs. And there is privacy because like we don't know what data is being used for training, and like for specifically for closed source models like GPT-4 and all, like we don't know what data is exactly used for the training stuff, which means there might be some of the privacy violations happening, which is a very highly intensive debate these days in the context of LLMs. I mean, the one of the minor issues of LLMs is like job displacements. Like LLMs are very good at like content creation and stuff, specifically generating images or writing essays and stuff, even like writing poems like Shakespeare, which we have seen a while back. So this might be an issue for artistic jobs in the future, which is also discussed. But like there is obviously a need of human who could curate those outputs as well. So we are close to the end of the session, and I would like to touch upon what exactly could be done next. Multimodal models is an interesting topic these days, or very trending topic these days, like with the evolution of GPT-4 and Gemini, where you could use text and image as prompts and like generate images or generate text. So interesting things are happening in multimodal models where you can gather up information from different modalities, as in like image, text, musics. You could see like even these days, like there you can write a text and generate a music out of that. So there are interesting things happening. I can recommend you to read upon these multimodal models these days, like for example Gemini and all, which could be very interesting if you are interested in pursuing something in LLMs. And also scaling up, like as we seen, like scaling up is a big thing for LLMs. You can get more resources, but it might be hard for us individually doing this scaling up things, but it's happening in the industry. So if you get a chance to work on something like scaling up is also an interesting thing to or an engineering challenge to make these LLMs work properly. And also the explainable AI, because like we know LLMs are black box right now. We don't know what exactly is happening inside. So having an understanding of what is happening inside, or maybe like having an explanation or a responsibility from the LLMs to justify the answer is sort of crucial in this aspect. So people are working on explainable AI, or we could say responsible AI or fairness and sort of things. So these are like some of the interesting things those are happening right now, and like there's a potential of exploding in these areas as well. So I hope you have had a very high level understanding of what LLMs are, and what we could do with LLMs. And there are a lot of sources online to read about and look around for to learn more about LLMs and contribute in the field of LLMs as well. And that brings to the end of our session. And I think that will pretty much it. If you have any questions, I think there is one question in the chat. If the data source is a tabular data set, what is the best way to build a conversational chatbot? Is retrieval augmented generation gives the best outcome for tabular data like text data? Generally, I believe tabular data, so text data is generally not considered a tabular data. Tabular data is basically you have like a table of columns of something, and then like you have numbers and values. Text data are like generally more of like unstructured data, where you just have text values. So text data can be easily used with LLMs, but I'm not exactly sure what you mean by tabular data to build a conversational bot. Mm, all right. The next question is, if you have several data sources, PDFs, SQL APIs with real-time data, what is the most appropriate way to, okay, this is more relevant, I guess. Way to build a conversational chatbot using LLM API keys. I want to convey that information that though I have like a sort of knowledge in LLMs and these things, I'm not sort of an engineering person, which I use LLMs for research purposes. So using LLM APIs is not my expertise, but I'll try to answer this question. If we have several data sources, what is the most appropriate way to build a conversational chatbot? So it could be basically I I think it's based on how you prompt the model. Like, for example, if you have a tabular data, you could maybe prompt the task to the LLM based on your tabular data in a text form, and then, or maybe like automate that process of prompting and give it to the LLM, because LLMs cannot process the tabular data. So you need a textual information. So basically, it has to be done with this prompt engineering, I guess. Yep. I hope that answers the question. And if we have no more questions, I think we could stop for now, right?
Yes, Afam. So we
Yeah.
will be continuing with session 2 as scheduled at 1 p.m. So we'll take a small break, and everyone you can stay in the meeting if you want, and you can log off and come back at 1. And we'll like do maybe like 2.5 more hours of diffusion models and like vision transformers and those things. Yeah, so Devnit will stop the recording for now, and then we'll start again after Kanchana joins. Thank you, everyone. And thank you, Afam and Abba, for the great session.
Thank you, everyone. Bye.